Hello there, and welcome to Science for Sleep, where curiosity can slow down, complicated ideas are given room to breathe, and the universe is explored without anyone being asked to sit an exam at the end. Tonight, we're turning our attention toward the outer regions of the Milky Way, far beyond the familiar stars that form the bright band across a dark sky. Out there, in a region that looks empty to human eyes, an enormous cloud of gas is moving toward our galaxy at extraordinary speed. It is called the Smith Cloud. The name may sound modest, perhaps like a patch of weather that might bring light rain before lunch, but the object itself is anything but modest. The Smith Cloud is a vast body of mostly hydrogen gas. It contains enough material to contribute to the formation of a very large number of new stars, and it stretches across thousands of light years. It does not glow like a star, it does not have a solid surface, and it cannot be seen by simply looking through an ordinary telescope. Astronomers found it by detecting radio waves released by neutral hydrogen, which means that this giant object remained hidden in a part of the sky people had studied for centuries. It is also moving quickly. The cloud is travelling through the halo of the Milky Way and heading toward the galaxy's disk. Current measurements indicate that it will meet the disk tens of millions of years from now. That is a long wait by human standards, but it is not especially long for a galaxy. The Milky Way has existed for more than 13 billion years, so a few tens of millions of years is closer to a brief appointment in its schedule. Fortunately, this is not an appointment anyone on Earth needs to worry about. The collision is expected to happen far from our part of the galaxy, and it will not arrive as a solid object striking the Milky Way like a stone hitting a window. It is gas meeting gas, shaped by gravity, pressure, magnetic fields, heat, and motion. Still, the word collision naturally gets our attention. When people hear that something enormous is racing toward the galaxy, the imagination tends to become very efficient. It may immediately produce explosions, damage planets, alarms, emergency meetings, and at least one scientist staring at a screen while saying, "That cannot be right." The actual story is less dramatic in the immediate sense, but much more interesting when we look closely. The Smith Cloud may carry material into the Milky Way that can eventually help form new stars. It may also be material that once belonged to the galaxy, was thrown outward, and is now returning. Astronomers have even compared its path to that of a boomerang, although this is a boomerang made of gas moving across distances so large that no one would want to be responsible for catching it. Before we go farther, where are you listening from tonight? Perhaps you're in a city where the night sky contains only a few visible stars. Maybe you are somewhere quieter, where the Milky Way can be seen as a pale band overhead. You might be listening late at night, early in the morning, or during an afternoon that has become unexpectedly suitable for learning about enormous hydrogen clouds. Wherever you are, take a moment to consider the sky above you. The stars we see are only the bright and obvious part of our galaxy. Between them, around them, and far beyond the main disk, there is gas that our eyes cannot detect. Some of it is thin and widely spread. Some of it gathers into clouds. Some moves along with the Milky Way's rotation, while some travels at speeds and in directions that make astronomers look twice. The Smith Cloud belongs to that last group. If you find this kind of calm exploration soothing, interesting or useful when you are trying to settle down, you can give the video a like and subscribe to the channel. It helps this quiet part of YouTube reach other people who might enjoy learning about the universe without being shouted at by it. You can also leave a comment telling us where you are listening from. There is something appropriate about people in many different places considering the same object, especially an object so large that ordinary ideas of place begin to feel a little limited. For now, get comfortable and picture the Milky Way from the side. Its main disk would look thin compared with its width, rather like a broad, flattened circle with a brighter central region. The sun sits inside that disk well away from the centre. Most of the stars, dust and cold gas that we associate with the galaxy are concentrated there. Above and below the disk lies the galactic halo, an enormous surrounding region containing dark matter, very hot gas, old stars, star clusters, and clouds moving on unusual paths. The Smith cloud is in this halo, below the plane of the galaxy, and it is moving upward toward the disk. The phrase "below the galaxy" is useful for describing a diagram, although space itself has no permanent up or down. If you turn the diagram over, the physics would remain entirely unconcerned. Astronomers choose directions so that positions can be described clearly, and the Smith cloud currently sits on one side of the disk, several thousand light-years from its dense central layer. Its motion has been studied well enough for researchers to estimate not only how fast it is travelling along our line of sight, but also how it is moving through three-dimensional space. That is more difficult than it may sound. When we observe a distant object, we usually see only a flat image on the sky. It is similar to watching a car from a great distance. You may be able to tell whether it is moving toward you or away from you, but judging its full path requires more information. With the Smith cloud, astronomers combined measurements of hydrogen gas, distance estimates, and the changing velocities seen across its structure. The result is a picture of a cloud moving at roughly 300 kilometers per second relative to the Milky Way. Converted into a more familiar form, that is more than 1 million kilometers per hour. At that speed, a journey from London to New York would take only a few seconds, provided we ignored the atmosphere, the ocean, every engineering limitation, and the rather serious problem of stopping at the other end. Yet the Smith cloud is not crossing an empty universe. It is pushing through the Milky Way's halo, where very thin gas still creates resistance. The cloud has a rounded leading region and a long trailing structure, giving it a shape that astronomers often describe as comet-like. This does not mean it is a comet. It has no rocky nucleus, no icy surface, and no neat tail produced by sunlight. Its shape appears to record the effects of movement through surrounding material. Gas is being compressed, disturbed, stripped, mixed, and possibly broken into smaller pieces. This raises an immediate question. How has it survived? A cold or relatively cool cloud moving through hotter, thinner gas should experience forces that gradually tear it apart. Computer simulations often show such clouds becoming unstable. Their edges ripple, material peels away, and the original body loses its identity. The Smith cloud has clearly been affected by this process, yet it remains recognizable as one enormous structure. Something about its history, composition, environment, or internal support has allowed a substantial part of it to continue moving toward the disk. Several explanations have been proposed. Perhaps the cloud began with more mass, and we are seeing what remains after a long period of erosion. It may be gathering additional gas as it travels. Magnetic fields might help organize or protect parts of it. Some researchers have explored whether it could be held within a small halo of dark matter, although evidence about its chemical composition has made the story more complicated. There is also the possibility that the cloud has not come from deep intergalactic space at all. It may have been expelled from the Milky Way in the past and is now falling back. That last possibility changed the way astronomers thought about the object. For years, one of the central questions was whether the Smith cloud represented fresh material arriving from outside the galaxy. Galaxies need gas if they are to continue making stars. A star forms when gas becomes dense enough for gravity to pull it together, eventually creating conditions hot and compressed enough for nuclear fusion to begin. The Milky Way has been forming stars for billions of years, but the supply of suitable gas is not unlimited. Some gas becomes locked inside stars, some is heated, some is pushed away by stellar winds and supernova explosions. If star formation is to continue over very long periods, galaxies must recycle material or acquire new supplies. A giant incoming cloud therefore looks important. If the Smith cloud were made from nearly pristine hydrogen that had never spent much time inside a galaxy, it could be part of the Milky Way's external fuel supply. If, however, it contains a significant abundance of heavier elements produced by stars, then it has probably been processed before. Astronomers use the word metals in a special way. In everyday life, metals include things such as iron, copper, and aluminium. In astronomy, almost every element heavier than hydrogen and helium is called a metal. Oxygen is a metal, carbon is a metal, sulfur is a metal. Astronomers are very good at studying the universe, although their naming system occasionally sounds as though the periodic table was sorted shortly before closing time. The chemical evidence from the Smith cloud points toward material that has already been enriched by stars. Researchers used ultraviolet observations of distant active galaxies located behind the cloud. These background objects acted like powerful lamps. Their light passed through the Smith cloud before reaching us, and atoms in the cloud absorb specific wavelengths. By studying the missing parts of the light, astronomers could identify elements in the gas and estimate their abundance. Sulfur was especially useful. The measurements show that the cloud contains a substantial amount of heavy elements, with an abundance consistent with gas from the outer Milky Way, rather than completely untouched material from intergalactic space. That finding supports a remarkable history. The Smith cloud may once have been part of the Milky Way's disk. Powerful activity, perhaps involving many supernovae and energetic stellar processes, could have pushed gas out into the halo. Once there, the gas continued moving under the influence of gravity and its interaction with the surrounding medium. Instead of escaping forever, it followed a long path and began returning. In this view, the cloud is part of a galactic fountain, a large-scale cycle in which gas rises from the disk, travels through the halo, cools, mixes with other material, and eventually falls back. The word fountain makes the process sound tidy. A real galactic fountain would not resemble a decorative stream of water in a quiet garden. It would involve hot gas driven by explosions, expanding bubbles, turbulent flows, magnetic fields, and material travelling for millions of years. There would be no central pump with a clearly labelled switch. Even so, the comparison is useful because the material goes up and comes down, carrying matter between the disk and the halo. The Smith cloud could be one especially large and visible part of that circulation. There are still uncertainties. Its mass is considerable. Its present speed and direction require explanation. Its long shape tells us that interaction with the halo is active, but the exact history recorded in that shape is difficult to reconstruct. The chemical measurements are important, yet mixing can complicate them. A cloud that began with one composition may collect gas from its surroundings and lose some of its own material. By the time astronomers study it, its chemical signature may be a blend rather than a clean label showing where it was born. This is one reason the Smith cloud matters beyond its size. It is a nearby laboratory for understanding how galaxies exchange gas with their surroundings. We cannot watch the full process from beginning to end because it unfolds over millions of years. Instead, we observe different pieces, measure their positions and velocities, study their chemistry, and use physical models to infer what happened before and what is likely to happen next. The cloud gives astronomers a chance to examine accretion, recycling, turbulence, and star-forming fuel in the galaxy we know best. It also helps correct a common picture of the Milky Way. A galaxy can look stable in an illustration. Spiral arms curve neatly around a bright centre. Stars occupy fixed-looking positions. The whole system appears complete, as though it were assembled long ago and has simply been rotating ever since. In reality, the Milky Way is active and changing. Stars are born and die. Gas is heated, cooled, expelled, and returned. Smaller galaxies interact with it. Streams of stars and gas stretch across its halo. Material enters, material leaves, and some of it apparently changes its mind halfway through. The Smith cloud is part of this ongoing movement. Its future meeting with the disk will not be a single clean moment. The outer layers are already interacting with the galactic environment. As it approaches denser regions, the pressure on the cloud will increase. Portions may slow down, fragment, heat up, or mix into the Milky Way's gas. Other parts may remain together longer. Over time, its material could contribute to large clouds in the disk, and those clouds may later take part in star formation. This does not mean that a group of stars will switch on immediately when the Smith cloud arrives. Star formation requires the right conditions. Gas must cool and become dense. Gravity must overcome pressure, turbulence, and magnetic support. The process can take time, and incoming material may be spread across a broad region. Estimates often suggest that the cloud contains enough gas to help form millions of stars comparable in mass to the Sun. But that comparison describes the available material, not a guaranteed delivery of millions of finished stars. Galaxies are not factories where hydrogen enters one door and neatly labelled suns leave through another. Even so, the arrival could influence the future of part of the Milky Way. The expected impact region lies far from the solar system. Earth will not pass through the main cloud, and the event is not considered a threat to life here. By the time it occurs, the night sky from Earth will have changed for many other reasons. Stars move. Constellations slowly lose their familiar shapes. The sun travels around the centre of the galaxy. Species appear and disappear. Continents shift. Tens of millions of years are enough for a great deal to happen, even if the Milky Way regards the interval as fairly ordinary. Thinking at that scale can be difficult, because our brains are built around days, seasons, and lifetimes. We understand a cloud moving toward us when it is visible outside a window. We understand speed when a car passes on a road. We understand distance when it can be crossed by walking, driving, or reluctantly changing trains. The Smith cloud does not fit those instincts. It is thousands of light years long. It moves at hundreds of kilometers per second. It will take millions of years to reach the disk. Every familiar measurement has to be enlarged until it becomes almost unusable. Astronomy deals with this problem by building understanding one measurement at a time. Radio telescopes map the hydrogen. Spectrographs separate light into wavelengths. Background sources reveal chemical fingerprints. Models calculate orbits. Simulations test how gas behaves when it moves through a halo. No single observation tells the entire story, but the pieces begin to agree on a broad picture. A huge, fast-moving cloud lies near the Milky Way. It is travelling toward the disk. It has probably interacted with the galaxy before, and it offers a rare view of the way galactic material circulates. Its ordinary name makes the contrast even better. The cloud was named after Gale Smith, the astronomer who identified it in radio observations while she was a graduate student in the early 1960s. It was not found because someone saw a spectacular object filling the sky. It appeared in data as unusual hydrogen emission, moving at a velocity that did not match the simple rotation expected in that direction. The discovery began with careful observation, a map, and a feature that refused to behave normally. That is often how important astronomical stories begin. Something does not fit. A point of light changes when it should remain steady. A planet moves slightly differently from a prediction. A spectrum contains an unexpected line. A cloud of hydrogen travels too quickly. The universe rarely provides a label explaining the answer. It provides an inconsistency and leaves people to investigate. In the case of the Smith cloud, the investigation has lasted for decades. Its distance had to be constrained. Its shape had to be mapped. Its mass had to be estimated. Its motion through 3 dimensions had to be reconstructed. Astronomers debated whether it came from outside the Milky Way, whether it belonged to a small dark matter system, whether it could survive passage through the disk, and whether it was returning material launched by the galaxy itself. Each new instrument added another piece. Radio observations showed the hydrogen structure. Optical measurements traced ionized gas. Ultraviolet spectroscopy revealed elements that ordinary images could not show. There is no need to rush toward the collision or decide immediately where the cloud came from. The most useful place to begin is with the strange fact that an object this large could remain unseen in a familiar sky. Settle into whatever position feels comfortable. Let the brightness of the screen become less important, and keep in mind that the empty spaces around a galaxy are not truly empty. They contain movement, heat, pressure, and material with a history. Somewhere beyond the bright disk, the Smith cloud continues along its measured path, while radio waves from its hydrogen cross-space and arrive at our instruments. Those radio waves were the first clear sign that something unusual was there, and understanding how they revealed the Smith cloud requires us to look at the sky in a way that has nothing to do with ordinary sight. Human eyes detect only a narrow range of electromagnetic radiation. We call that range visible light because, rather conveniently, it is the part we can see. Red sits near one end, violet near the other, and between them lies every colour that has ever appeared in a rainbow, a traffic light, or a disagreement about whether a shirt is blue or green. Outside that small visible range, however, the electromagnetic spectrum continues in both directions. There are shorter wavelengths, including ultraviolet light, X-rays and gamma rays. There are also longer wavelengths, including infrared radiation, microwaves, and radio waves. These are all forms of light. They differ in wavelength, frequency, and energy, but they belong to the same electromagnetic family. Radio waves are not sound travelling through space. They do not need air, and they are not cosmic broadcasts that can be heard by placing a receiver near a window. They are electromagnetic signals that can be collected, measured, and converted into information. Visible light telescopes use mirrors or lenses to collect the wavelengths our eyes recognise. Radio telescopes perform a similar job with much longer wavelengths. Their large metal dishes collect faint radio signals and direct them towards sensitive receivers. Computers then record the strength and frequency of the incoming radiation. The result may later be turned into a graph, a map, or a false colour image, but the colours in such an image are usually assigned by scientists. The Smith cloud is sometimes shown in bright reds, oranges, blues, or purples, yet the cloud itself would not look like a coloured stain in the sky. Those colours represent measured radio intensity or velocity. They help researchers see structure that would otherwise remain hidden inside columns of numbers. The particular radio signal that exposed the Smith cloud comes from neutral atomic hydrogen. Hydrogen is the simplest and most common element in the universe. A neutral hydrogen atom contains one proton and one electron. That seems straightforward, although quantum mechanics rarely allows anything to remain straightforward for very long. The proton and electron each possess a quantum property known as spin. Spin is not quite the same as a small object physically rotating despite the name. It behaves more like an intrinsic form of angular momentum. The proton and electron can occupy a slightly higher energy arrangement when their spins are aligned, or a slightly lower energy arrangement when they point in opposite directions. Very occasionally, the electron changes from the higher energy state to the low energy state. When that happens, the atom releases a photon with a wavelength of about 21 centimeters and a frequency of roughly 1420 megahertz. The energy involved is extremely small. A single hydrogen atom can remain in its higher energy state for millions of years before making this transition. If an astronomer had to wait beside one atom for it to produce a signal, radio astronomy might have developed at a rather discouraging pace. Space, fortunately, contains a great deal of hydrogen. When an enormous cloud contains vast numbers of neutral atoms, transitions are occurring somewhere within it all the time. The combined emission becomes detectable, even when the gas is cold, thin, and completely dark at visible wavelengths. The 21 centimeter line therefore gives astronomers a powerful way to map neutral hydrogen across the Milky Way and beyond. The signal is also useful, because radio waves at this wavelength can travel through regions that block visible light. Interstellar dust absorbs and scatters ordinary starlight, hiding parts of the galaxy behind dark lanes. 21 centimeter radiation passes through much of that dust, allowing radio telescopes to examine hydrogen on the other side. By the middle of the 20th century, astronomers had begun using this signal to study the structure and rotation of the Milky Way. The first successful detection of the 21 centimeter hydrogen line took place in 1951. That discovery opened a new method of examining the galaxy, particularly regions where stars and dust made visible observations incomplete. Radio astronomers pointed their instruments at different parts of the sky and recorded the intensity of the hydrogen signal at a range of frequencies. Those frequency measurements revealed more than the location of gas. They also showed how quickly it was moving toward or away from Earth. The reason is the Doppler effect. You have probably noticed the Doppler effect when an ambulance passes. The siren sounds higher as the vehicle approaches and lower after it moves away. The siren itself has not suddenly changed its opinion about the correct note. The motion of the source compresses the sound waves in front of it and stretches them behind it. Light behaves in a related way. When a source moves toward us, its light shifts toward shorter wavelengths and higher frequencies. When it moves away, the light shifts toward longer wavelengths and lower frequencies. For hydrogen emitting at 21 centimeters, even a slight shift in the measured frequency can reveal the gas's motion along our line of sight. Astronomers know the natural frequency of the hydrogen transition with great precision. They compare that expected value with the value received by the telescope, and the difference can be converted into velocity. This means a radio survey can produce something more informative than a flat picture. Imagine pointing a telescope at one location in the sky. The receiver may detect hydrogen at several different velocities. One component could belong to gas rotating normally within the Milky Way's disk. Another could come from a nearby cloud. A third might be moving so quickly that it stands apart from the expected pattern. Researchers can separate those components by frequency. They can then create maps showing only gas within a selected velocity range. It is rather like listening to a crowded room and discovering that, with the right equipment, you can isolate every conversation according to how quickly each speaker is walking away from you. This was the observational world in which Gail Smith made a discovery. In the early 1960s, Smith was a graduate student studying radio astronomy in the Netherlands. She was examining neutral hydrogen emission from the Milky Way, using the 21 centimeter line to investigate the distribution and motion of galactic gas. At first glance, the data contained the sort of features astronomers expected to see. Hydrogen within the disk follows the general rotation of the galaxy. Since the Sun is also moving around the galactic center, the velocities measured from Earth vary depending on which direction the telescope is pointed. The Milky Way's rotation does not produce one identical signal across the whole sky. Instead, it creates organized patterns that can be predicted and modeled. Smith noticed a feature that did not fit comfortably into those patterns. The signal appeared in the direction of the constellation Aquila, but the hydrogen responsible for it was travelling at an unusual radial velocity. It was moving much faster than ordinary gas in that direction should have been moving if it were simply taking part in the standard rotation of the disk. The cloud's velocity relative to the local standard of rest was close to 100 kilometers per second in the direction of Earth, although the precise number changes across the object and depends on the reference frame being used. That phrase, local standard of rest, sounds like a designated area in which astronomers are encouraged to sit quietly. It is actually a reference system designed to remove much of the Sun's own motion when comparing velocities inside the Milky Way. Earth travels around the Sun. The Sun moves relative to nearby stars. The entire solar system orbits the center of the galaxy. An observed velocity therefore depends partly on the motion of the observer. Astronomers correct for those movements so they can compare the gas more meaningfully with the average motion of material near the Sun. Even after those corrections, the feature Smith identified remained unusually fast. This placed it among a class of objects that had only recently begun attracting serious attention: high-velocity clouds. A high-velocity cloud is a concentration of gas whose observed motion cannot be explained easily by the regular rotation of the Milky Way. The exact classification depends on the method and the region being studied, but the central idea is simple. The cloud is not moving the way nearby galactic gas is expected to move. That difference makes such clouds easy to distinguish in velocity data, even when they overlap ordinary Milky Way gas on the sky. Consider two transparent sheets placed on top of each other. One contains a drawing of the galactic disk, while the other contains the Smith cloud. In an ordinary image, their features may overlap and become difficult to separate. Radiospectroscopy adds velocity as another dimension. The disk gas appears at one set of frequencies, while the faster cloud appears at another. Astronomers can select the unusual frequencies and remove much of the foreground confusion. The hidden cloud then becomes visible as a radio structure. Smith reported the peculiar hydrogen feature in 1963. At the time, its true distance was not known, and that created an enormous uncertainty about almost everything else. An object's apparent size tells us only how much of the sky it covers. Its physical size depends on its distance. A small cloud nearby and a huge cloud far away can have the same apparent width. Hold a coin close to your eye, and it can cover the moon. This does not mean the coin has had a particularly successful evening and grown to lunar proportions. The same issue affects mass estimates. Astronomers can measure the concentration of neutral hydrogen along a line of sight, but calculating the cloud's total mass requires knowing the physical area it covers. Without a reliable distance, a cloud might be a modest local feature or an enormous object in the galactic halo. For decades, that uncertainty followed the Smith cloud. Researchers knew where it appeared. They knew its hydrogen was moving at high speed. They could map parts of its radio emission. Yet its location in three-dimensional space remained difficult to establish. The Milky Way gives us a poor viewing position for studying itself. We are embedded inside the disk, surrounded by stars, gas and dust. Mapping the galaxy from Earth is a little like trying to understand the layout of a large forest while standing among the trees. You can measure directions and distances to selected objects, but you cannot step outside for a convenient overhead photograph. The Smith cloud added another difficulty because it contained no obvious group of stars that could serve as distance markers. Stars can sometimes be placed at known or estimated distances through their brightness, spectra, or geometric parallax. A mostly starless gas cloud offers fewer direct clues. Its hydrogen emission tells us its direction and radial velocity, but not automatically how far away it is. Early observations therefore left several possibilities open. The cloud could have been relatively near the Sun. It could have been part of the Milky Way's distant halo. It might even have been an object much farther away, although later evidence would rule out the more extreme options. Its strange velocity also invited different explanations. Perhaps it was falling into the galaxy. Perhaps it had been thrown out of the disk. Perhaps it was associated with a small, unseen companion of the Milky Way. Perhaps its apparent speed was being misunderstood because its distance and full three-dimensional motion were unknown. Radio observations could identify the ghost, but they could not immediately provide its address or biography. What they did provide was a growing picture of its structure. As surveys improved, astronomers found that the Smith cloud was not a simple round patch. It extended across a large region of the sky, with different concentrations of hydrogen appearing at related velocities. A cloud of gas does not have a sharp boundary like a planet. Its density gradually declines into its surroundings, and different observations may detect different portions depending on the sensitivity of the telescope. Brighter regions are easier to map. Fainter extensions may remain unnoticed until a more sensitive instrument surveys them. Two astronomers using different detection limits might therefore quote different sizes without either one being careless. This is especially important for the Smith cloud because much of its story is written in low-density gas. The densest neutral hydrogen forms its most obvious structure. Around it lies more diffuse material, some of which may be ionized rather than neutral. Beyond that, fragments and streams may be mixing into the Milky Way's halo. 21-centimeter observations detect only neutral atomic hydrogen. They do not directly count ionized hydrogen, in which the electron has been separated from the proton. They also do not automatically reveal helium, metals, dark matter, or every warmer phase of gas surrounding the cloud. The radio map is therefore extremely valuable, but it is not a complete inventory. It is similar to mapping a city at night by recording only the buildings with their kitchen lights on. The resulting image would show genuine structures and patterns, but it would not contain every resident, wall, road, or room. Despite that limitation, neutral hydrogen supplied enough information to show that the Smith cloud was exceptional. Later radio maps revealed a broad leading region and an extended tail. The head appeared to point in the direction of motion, while material behind it stretched away across the sky. Such head-tail structures are often signs of interaction. A gas cloud travelling through a surrounding medium experiences pressure on its leading surface. Material can be compressed at the front and stripped from the sides or rear. The process is called ram pressure stripping. The name may suggest an unusually determined farm animal, but it refers to pressure produced by motion through gas. The faster the cloud moves, and the denser the surrounding material becomes, the stronger that pressure can be. Even the thin gas of the galactic halo matters when an object is large, diffuse, and travelling for millions of years. The Smith cloud's shape suggested that it was not drifting through an empty region. It was meeting resistance, losing material, and changing as it moved. Radio data also showed variations in velocity along the cloud. Different portions were not all travelling in exactly the same way. Some of that variation could come from the cloud's orientation. If one end points more toward us than another, their measured radial velocities will differ even if the structure is moving together. Other differences may reflect genuine disturbances. Gas stripped from the main body can slow down as it mixes with the surrounding halo. Shocked or compressed regions may develop separate velocity components. Fragments can begin following slightly different paths. By examining these changes, astronomers began reconstructing the direction in which the cloud was travelling. This required careful interpretation. A tail on a map does not always point neatly opposite an object's motion. Magnetic fields, density variations, turbulence, and the rotation of the galactic environment can alter the shape. Still, the overall evidence supported the view that the denser end was leading, and that the cloud was travelling toward the plane of the Milky Way. For a long time, the Smith cloud remained a known object without a well-known scale. It appeared in catalogues of high-velocity gas and was studied by researchers interested in the halo, but its full importance was difficult to judge. A cloud with no reliable distance is surrounded by question marks. Then radio astronomy gained a much larger and more sensitive instrument, the Robert C. Byrd Green Bank Telescope in West Virginia. The Green Bank Telescope has a collecting surface roughly 100 meters across. It is fully steerable, allowing it to point toward different regions of the sky while gathering extremely faint radio emission. Its unusual design places the support structure away from the direct path of incoming radiation. This reduces unwanted reflections and improves the quality of measurements, particularly when astronomers are searching for weak extended signals. In the mid-2000s, Felix Lockman and his colleagues used the Green Bank telescope to study the Smith cloud in much greater detail. The new observations did not rediscover the cloud. Gail Smith's original detection had been recognized for decades. What the Green Bank data provided was a clearer and more complete radio map, sensitive enough to follow faint hydrogen across the structure, and precise enough to measure how its velocity changed from place to place. The resulting image looked strikingly like a comet. There was a denser head, a broad body, and a long trail of gas extending behind it. Smaller pieces appeared around the main structure. Some regions seemed connected to slower gas associated with the Milky Way, offering evidence that the cloud was already interacting with galactic material. This was an important development because interaction could help determine distance. The Milky Way's gas rotates around the galactic center, and the expected velocity varies with position. If material from the Smith cloud is physically colliding and mixing with known galactic gas, the observed velocities can be compared with models of the galaxy's rotation. Lockman and his colleagues used these relationships together with other evidence to estimate that the cloud was about 12 kiloparsecs from the Sun, or roughly 40,000 light-years away. That distance placed it well within the Milky Way's halo rather than in some remote intergalactic location. Its leading tip was less than 10,000 light-years below the galactic plane, although its full structure extended much farther across the sky. Once a distance was available, the cloud's apparent dimensions could be converted into physical dimensions. The faint radio feature detected decades earlier became an object more than 3 kiloparsecs long. A single kiloparsec equals about 3,260 light-years. The Smith cloud therefore spans more than 10,000 light-years from end to end, depending on which faint extensions are included. It is wider than many people expect any object called a cloud to be. The word usually brings to mind something that passes over a neighbourhood, delays a picnic and moves on. This cloud could stretch across a substantial fraction of the distance between the Sun and the centre of the Milky Way. Its neutral hydrogen mass could also be estimated. The measurements indicated more than 1 million times the mass of the Sun in neutral atomic hydrogen alone. Additional ionized gas increases the total. The Smith cloud is not simply one uniform lump of cold hydrogen. It includes gas in different physical states, much of which cannot be measured through the 21-centimetre line. The improved radio map also made its velocity more meaningful. Its motion along our line of sight had been known since the discovery, but the cloud's orientation and interaction patterns helped researchers estimate its movement across the sky and toward the galactic plane. The leading section was travelling through the Milky Way's frame at close to 300 kilometers per second. Most of that motion followed the direction of galactic rotation, while a smaller but important component carried it upward toward the disk. In other words, the Smith cloud is not diving straight into the Milky Way from above. It is moving along with the galaxy to some extent, approaching the disk at an angle, while travelling rapidly around the galactic centre. That distinction matters because a cloud's survival and future path depend on the direction of its motion. Gas striking the disk head-on would experience different conditions from gas arriving at a shallow angle. The radio observations also indicated that the cloud was shedding material before reaching the main disk. Some of its gas appeared to be slowing and joining the surrounding Milky Way environment. The ghost was leaving a trail. Nothing about the discovery required the cloud to shine in visible light. No photograph showed its edge against a black background. No astronomer watched it cross the stars from one night to the next. Instead, its existence emerged from a narrow radio signal, shifted in frequency by motion. Its structure emerged from thousands of telescope pointings. Its direction emerged from differences in velocity across the map. Its distance emerged from the way its gas appeared to interact with the rotating Milky Way. This is one of the quiet strengths of astronomy. An object does not need to be bright or close to provide evidence. It only needs to influence some form of radiation in a way instruments can measure. The Smith cloud released 21-centimetre photons long before anyone knew they were travelling toward Earth. Those photons crossed thousands of light-years, entered radio receivers, and became electrical signals. The signals were recorded as spectra. The spectra were compared, mapped, and interpreted until an invisible cloud acquired a position, a shape, a mass, and a likely path. Even now, the radio images should not be mistaken for ordinary photographs. When the Smith cloud appears against a visible picture of the Milky Way, two different kinds of data have usually been combined. The stars come from optical observations. The coloured cloud comes from radio measurements. This combination helps us understand where the cloud lies on the sky, but it also creates the impression that a person with sufficiently good eyesight might see it floating among the stars. They could not. Neutral hydrogen at the cloud's density produces very little visible emission. Even though the object covers a broad area of the sky, its gas is too thin and too dim for human eyes. If radio vision were added to our natural senses, the night sky would look very different. Neutral hydrogen would reveal huge structures across the Milky Way. Spiral features would become easier to trace. High-velocity clouds would appear above and below the disk. the Smith cloud would occupy an area roughly as wide as an outstretched hand held at arm's length. The full moon would look small beside it. That comparison refers to apparent size, not brightness. A faint object can cover a large patch of sky without being noticeable. The Smith cloud is enormous in angle and almost perfectly hidden in visible light. Its discovery therefore depended on someone looking at the right kind of data and recognizing that an unusual velocity deserved attention. Gail Smith did not know, when she recorded that feature, that later observations would reveal a cloud thousands of light-years long. She could not yet know its distance, its mass, its trajectory, or the debate that would develop around its origin. What she had was a signal that did not match the expected behaviour of galactic hydrogen. That was enough. Scientific discoveries are often described after the fact as though the answer appeared all at once. In reality, they tend to arrive in stages. First comes an observation, then comes uncertainty. Other researchers test it, new instruments improve it, and explanations compete. The Smith cloud moved through that process for more than half a century. The 1963 detection established that the gas existed. Later surveys outlined its extent. The Greenbank telescope exposed its comet-like shape and interaction with the halo. Distance measurements gave it a physical scale. Ultraviolet observations would eventually add chemical information and suggest where it had been before. Each method examined a different aspect of the same object. Radiolight remained the foundation because hydrogen is the largest visible component of the cloud. Without the 21 centimeter signal, astronomers might know that some ionized material existed in that direction. But the Smith cloud would be far harder to recognize as one connected high-velocity structure. The same radio signal that revealed its outline also gave clues to its internal condition. The width of a hydrogen spectral line contains information about the range of velocities within the telescope beam. A narrow line can indicate relatively cool or orderly gas. A broader line may result from higher temperature, turbulence, several overlapping components, or some combination of all three. Across the Smith cloud, astronomers find complex profiles rather than one perfectly clean peak. That complexity fits an object being disturbed by its environment. Some parts remain dense and neutral, others have been heated or ionized, some appear detached, some are decelerating as they interact with the halo. The cloud's radio image is therefore not a still portrait. It is a record of movement and damage, although interpreting that record requires models of gas dynamics rather than simply looking at its shape. There was also a larger reason high-velocity hydrogen attracted attention. The Milky Way continues forming stars, and stars require gas. Yet gas within the disk is gradually consumed, expelled, heated, and rearranged. Astronomers need to understand how the supply is renewed. High-velocity clouds may provide part of the answer. Some could carry fresh gas toward the galaxy. Others may return material previously expelled by stars and supernovae. Still others may be debris from interactions with smaller galaxies. Radio telescopes reveal where the neutral portion of the gas is located and how it moves. The Smith cloud became especially useful because its distance and three-dimensional trajectory could be constrained more clearly than those of most other high-velocity clouds. It went from being a peculiar feature in a survey to one of the best-studied examples of gas approaching the Milky Way. That transition took decades, and it depended on instruments becoming sensitive enough to detect its faint extensions. The cloud had not changed from obscure to important because it suddenly began moving faster or became larger. Our ability to measure it changed. This is worth remembering whenever an astronomical object is described as newly discovered. The object may have existed for millions or billions of years. The word new usually refers to human awareness, which is a much shorter and more easily surprised phenomenon. By the time astronomers created detailed Greenbank maps, the Smith cloud's radio signal had already travelled for roughly 40,000 years. The photons reaching the telescope showed the cloud as it was when much of recorded human history had not yet occurred. It has continued moving during the time its light has travelled to us, but 40,000 years is small compared with the tens of millions of years remaining before it reaches the disk. Our information is delayed, yet the broad prediction remains useful. The cloud is not going to make a sudden turn during the next human lifetime and arrive ahead of schedule. Galactic gas dynamics can be complicated, but not usually in the manner of a delivery driver who's found a shortcut. The important change was that radio observations had transformed a hidden signal into a measurable body with a direction of travel. With its radio form now visible, the question was no longer whether something unusual was moving through the halo. The question was what kind of object could stretch for thousands of light years, contain millions of solar masses of gas, survive at such speed, and still remain almost completely invisible to the human eye. The simplest answer is that the Smith cloud is an enormous collection of hydrogen located in the lower halo of the Milky Way. That description is correct, but it leaves out most of what makes the object unusual. It does not explain why the cloud is there, how it became so large, what keeps part of it together, or whether the material began inside our galaxy or arrived from somewhere beyond it. To understand the scale of the object, imagine placing it next to familiar parts of the Milky Way. The cloud is approximately 11,000 light-years long and around 2,500 light-years across, although its faint boundaries are difficult to define precisely. Light could leave one end of its main structure, travel for thousands of years and still not have reached the other end. The distance from the Sun to the nearest star system is just over 4 light-years. The Smith cloud is therefore long enough to contain that distance more than 2,000 times. It is larger than many of the structures we normally picture when we think about star-forming gas. It is also larger than some small galaxies, at least in physical extent. The important difference is that the Smith cloud does not contain a clearly detected population of stars arranged into a galaxy. It is mainly gas, spread so thinly that it remains transparent and dark in visible light. The phrase millions of solar masses can be misleading if we imagine all that matter compressed into a ball. The cloud's neutral hydrogen alone has a mass greater than 1 million suns. There is also ionized hydrogen surrounding and mixed with the neutral gas, which raises the total gaseous mass. Yet this material occupies an immense volume. Most of the atoms are separated by distances that would count as a very good attempt at personal space. A container holding ordinary air on Earth may contain trillions upon trillions of molecules in every cubic centimetre. In much of the Smith cloud, a cubic centimetre may contain far fewer than 1 hydrogen atom on average. That does not mean part of an atom has been carelessly divided. It means that if we measured a large enough volume and averaged the atoms within it, the density would be less than 1 atom per cubic centimetre. This low density explains why the cloud is invisible even though it is enormous. Brightness does not depend only on size or total mass. It also depends on how concentrated the material is, how hot it is, and what kinds of radiation it can produce. A large volume of thin hydrogen can contain an extraordinary amount of matter while emitting very little visible light from any one direction. There are faint forms of optical emission associated with parts of the cloud. Ionized hydrogen can produce a weak red line known as hydrogen alpha, and astronomers can detect it with sufficiently sensitive instruments. That is very different from an object bright enough to see with the eye. If the Smith cloud were visible at the same apparent boundaries shown in radio maps, it would cover a region of the sky many times wider than the full moon. Some comparisons place its apparent length at roughly 30 full moon diameters. That sounds as though it should dominate the night sky. Instead, a person can look directly toward it without seeing anything unusual. The cloud is not hidden behind a curtain. It is hidden by low surface brightness. A large sheet of clean glass can cover an entire window while remaining difficult to notice. The Smith cloud is not glass, but the comparison helps. Its atoms are distributed so sparsely that visible light from background stars passes through with only small measurable changes. Radio telescopes notice the hydrogen because the atoms produce 21 centimetre radiation. ultraviolet instruments notice the cloud because certain elements absorb narrow parts of the light passing through it. Human eyes notice neither effect. This creates a peculiar contrast. The Smith cloud is one of the largest distinct gas structures near the Milky Way's disk, yet it was discovered only after astronomers learned how to map an invisible wavelength. Its shape adds to the impression that we are looking at something caught in the middle of an event. The radio maps show a denser leading region followed by a long disturbed tail. Smaller fragments lie around the main body. Some gas appears to have been stripped away and slowed by contact with the surrounding halo. There is no hard outer shell. The cloud becomes thinner toward its edges and blends into its environment. Parts of it are neutral, parts are ionized, and some may already be mixed with Milky Way gas. Calling it one cloud is useful, but the name should not make us picture one perfectly connected object. It is closer to a moving complex of gas with a recognizable main body and a collection of related structures. The front, middle, and tail have experienced different conditions. They may also have different chemical mixtures because the trailing material has had more opportunity to interact with the halo. This complexity matters when astronomers try to determine where the cloud came from. A moving object usually carries clues to its history. Its direction can point back toward a starting region. Its speed can indicate how much energy launched it or how far gravity has pulled it. Its chemical composition can reveal whether its material has passed through stars. With the Smith cloud, those clues do not all lead to an easy answer. Its present trajectory suggests a close connection with the Milky Way. The cloud is moving in the same general direction as the galaxy's rotation, although not at the same speed or in exactly the same plane. This prograde motion is easier to explain if the material originated in the disk than if it arrived from a random direction in intergalactic space. It has retained a considerable amount of angular motion around the galactic center. At the same time, its mass and velocity make a simple launch from the disk difficult to arrange. Moving several million solar masses of gas out of a galaxy requires a great deal of energy. The cloud would also need to remain coherent while passing through hot halo gas. If it crossed the galactic disk during an earlier part of its orbit, survival becomes an even more serious question. For many years, astronomers considered three broad possibilities. The Smith cloud might be fresh gas falling into the Milky Way from outside. It might be the gaseous remains of a small, dark matter-dominated galaxy. Or it might be material expelled from the Milky Way and now returning through a galactic fountain. Each explanation could account for some features, and each created new problems. The first possibility was especially attractive because galaxies need incoming gas. The Milky Way forms new stars at a rate of roughly a few solar masses each year, depending on how the measurement is made. That process consumes cold gas. If the galaxy relied only on the material already in its star-forming disk, its supply would gradually decline. Astronomers therefore expect some gas to enter from the surrounding halo and the wider intergalactic environment. High-velocity clouds appear to be one route by which that material arrives. The Smith cloud seemed like an excellent candidate. It was large, mostly gaseous, moving toward the disk and not accompanied by an obvious stellar population. Perhaps it was a surviving lump of material from the space between galaxies. It might have been falling toward the Milky Way for billions of years, pulled inward by gravity and finally approaching the disk. Fresh intergalactic gas should have a distinctive chemical signature. The early universe produced mostly hydrogen and helium, with small traces of a few lighter elements. Elements such as carbon, oxygen, silicon, sulfur, and iron were made later inside stars or during stellar explosions. A cloud that had remained largely outside galaxies would generally contain fewer of these heavier elements. A cloud that had lived inside the Milky Way would be more chemically enriched because generations of stars had released processed material into the surrounding gas. Astronomers describe the abundance of elements heavier than hydrogen and helium as metallicity. The terminology is broader than ordinary speech. Oxygen counts as a metal in astronomy, despite being unsuitable for building a saucepan. Sulfur is also treated as a metal, even though no one is likely to request sulfur fittings during a kitchen renovation. Metallicity acts as a historical marker. It does not provide a complete address, but it can distinguish nearly pristine gas from material that has spent time in a star-forming galaxy. For years, researchers lacked a reliable measurement of the Smith cloud's metallicity. Neutral hydrogen was easy to trace in radio light, but detecting small quantities of heavier elements required another method. The cloud could not be examined by collecting a sample. It is tens of thousands of light-years away and has no convenient surface on which to land. Instead, astronomers used distant active galaxies as background lights. An active galactic nucleus is the extremely bright central region of a distant galaxy, powered by matter falling toward a supermassive black hole. Some of these objects are so luminous that their light remains detectable across billions of light-years. A few lie in directions that place the Smith cloud between them and Earth. The active galaxies are not physically connected to the cloud. They are far behind it from our point of view. Their light passes through the Smith cloud before reaching the Hubble Space Telescope. As that light travels through the gas, atoms and ions remove very specific ultraviolet wavelengths. Each element produces its own pattern of absorption lines, rather like a barcode. Hubble's cosmic origins spectrograph separated the incoming ultraviolet light into a spectrum. Researchers then looked for absorption, associated with the same velocities seen in the cloud's radiohydrogen. Matching the velocities was essential. There is gas in many parts of the Milky Way, and the light from a distant active galaxy passes through more than one region before reaching us. An absorption line by itself does not prove that the Smith cloud caused it. The unusual speed of the cloud provided a useful identifier. When sulfur absorption appeared at the same high velocity as the 21 centimeter hydrogen signal, astronomers could link the two with much greater confidence. The measurements focus particularly on ionized sulfur. Sulfur is valuable because it is created by stars and tends not to become heavily locked inside dust grains, compared with some other elements. The researchers compared the amount of sulfur with the amount of hydrogen along 3 lines of sight through the cloud. They also applied corrections for gas that was ionized rather than neutral. Their average result was a sulfur abundance of about half the solar value. That was far too enriched for a simple picture of untouched intergalactic hydrogen. The measurement suggested that the Smith cloud contained material processed by stars. Its metallicity also resembled the expected composition of the Milky Way's outer disk, where the abundance of heavy elements is lower than it is near the galactic centre. The chemical evidence gave strong support to a galactic origin. In the resulting model, the Smith cloud began near the outer Milky Way. Gas was pushed out of the disk approximately 70 million years ago, followed a long orbit through the halo and is now returning. The path resembles a broad arc rather than a straight line. The cloud moved away from the plane, reached a turning region under the influence of gravity, and began travelling back toward the disk. This is why the object is often described as a boomerang. The comparison is imperfect. An ordinary boomerang remains solid, completes its flight in seconds, and is normally thrown by someone who can see where it went. The Smith cloud is a changing mass of gas. Its journey lasts around 100 million years, and the identity of whatever launched it remains unknown. The metallicity result answered one question more strongly than it answered another. It made a purely pristine origin less likely, but it did not explain how the Milky Way removed so much gas from its disk. A cluster of massive stars can inject enormous energy into the interstellar medium. Their winds push against nearby gas, and their deaths as supernovae create expanding shock waves. When many massive stars form in the same region, their combined activity can carve a cavity called a superbubble. Hot gas inside the superbubble expands and may break out of the disk, carrying cooler material into the halo. This forms part of the galactic fountain process. Gas rises, interacts with the surrounding hot corona, cools, and eventually falls back. Some of the rising material may trigger additional cooling in the halo, collecting gas that was already there. That last detail could help explain the Smith cloud's large mass. the cloud we see today may not contain exactly the same atoms that left the disk. A smaller enriched outflow could have moved through the corona, causing some of the hot halo gas to cool and join it. Its present mass would then be greater than its launch mass. The observed metallicity would represent a mixture of disk material and halo material rather than one untouched sample. Models of a galactic fountain can reproduce parts of the Smith cloud's location and motion. Some place its starting region near the Perseus spiral arm in the outer disk. A vertical launch can reproduce the broad trajectory, but may not naturally produce the observed comet-like orientation. Researchers have therefore tested inclined ejections and high-speed winds emerging from superbubbles. These scenarios require substantial energy, but not necessarily an impossible amount for a large region of intense star formation. The absence of an obvious launch site today is not surprising. 70 million years is enough time for a stellar association to change considerably. The most massive stars would have died long ago. The original gas structure would have dispersed. Galactic rotation would have moved the region around the centre, and the spiral pattern itself may have evolved. We should not expect to look at one place in the disk and find a large sign reading "Smith Cloud launched here." Another explanation once received serious attention because it helped with the survival problem. Perhaps the Smith Cloud was held together by dark matter. Dark matter does not emit or absorb ordinary light in the usual way, but its gravity affects stars and gas. Galaxies contain large dark matter halos, and smaller concentrations of dark matter can surround dwarf galaxies. Some cosmological models predict that the Milky Way should be accompanied by many small dark matter subhalos. Not all of them would necessarily contain enough stars to become obvious dwarf galaxies. The Smith Cloud might therefore have been a failed galaxy, a dark matter halo containing gas but few or no stars. The invisible gravitational framework could help bind the cloud, allowing it to resist disruption while travelling through the Milky Way's hot corona. It might even help it survive an earlier crossing of the galactic disk. Computer simulations show that gas protected by a sufficiently massive dark matter halo could retain more of its structure than an unsupported cloud. Models without dark matter often required a much larger initial gas mass, or showed the object being severely disrupted. This made the idea attractive. It provided a possible explanation for how such a diffuse object had remained recognizable after a difficult journey. The theory also created observational questions. A dark matter subhalo would add mass without adding light. Astronomers could not simply photograph it. They would need to search for its gravitational effects or for indirect signals associated with some theoretical dark matter particles. Researchers used observations from the Fermi Gamma Ray Space Telescope to look for gamma rays from the cloud's region. Certain dark matter models predict that particle interactions could produce such radiation. No significant gamma ray signal from a dark matter core was detected. This did not prove that no dark matter existed, because the result depended on assumptions about the type and behaviour of the particles. It did place limits on some models. The metallicity measurement complicated the failed galaxy explanation more directly. A small, starless system arriving from outside the Milky Way should not naturally contain gas, enriched to around half the Sun's sulfur abundance. It could acquire enriched gas during a passage through the disk, but then the theory begins to change. Instead of a pristine gaseous dwarf entering the galaxy, we might have a dark matter concentration that crossed the Milky Way, collected disk material and carried some of it into the halo. NASA's description of the 2016 Hubble result raised this possibility. A dark object may have passed through the disk and captured Milky Way gas. That version preserves a role for dark matter, while accepting that much of the visible gas came from the galaxy. It remains speculative. There is no direct detection of a dark matter halo around the Smith Cloud. The third broad possibility, recycled galactic gas, currently fits the chemical evidence more naturally. Even that interpretation should not be treated as a perfectly completed case. The abundance measurement came from only a few lines of sight. The cloud is enormous and not necessarily chemically uniform. One beam may pass through its denser body, another through a disturbed edge, and another through a tail containing a greater amount of mixed halo gas. Each can produce a different result. Later simulations have shown that mixing may alter the metallicity measured in the cloud's wake. Gas stripped from the cloud blends with gas from the Milky Way's corona. If the halo material is more metal-rich or more metal-poor than the original cloud, the observed abundance will shift accordingly. In some simulated cases, material in the tail can contain roughly equal contributions from the original cloud and the surrounding halo. A spectrum taken through that region would not provide a pure sample of either one. This means that half-solar sulfur does not necessarily prove that every part of the Smith cloud began in the outer disk. The cloud could have started with lower metallicity and become enriched through mixing. Alternatively, it could have started with higher metallicity and been diluted by lower metallicity halo gas. Astronomers must model the mixing, ionization, dust content, temperature, and geometry before translating one chemical measurement into an origin story. More recent observations have added to the complexity by finding variations between elements and between different positions. Nitrogen-based estimates, sulfur measurements, and evidence for dust do not always produce one simple, uniform chemical picture. That does not erase the earlier result. It shows that the Smith cloud has been processed and mixed. The presence of dust is especially interesting because dust grains form from heavier elements and are common in galactic interstellar gas. Detecting depletion, where elements such as silicon are missing from the gas phase because they have become trapped in dust, provides another clue that at least some of the material has a galactic history. A completely pristine hydrogen cloud would not arrive carrying a normal supply of interstellar dust. Yet dust can also be acquired if a cloud passes through the disk or mixes with enriched halo material. Once again, the evidence points toward contact with the Milky Way but does not provide a simple birth certificate. The Smith cloud may therefore have more than one meaningful origin. Its gas may come from several sources. Some could have been expelled from the outer disk. Some may have condensed from the hot corona. Some may have been collected during earlier interactions. If a dark matter concentration is involved, it could have provided the gravitational structure around which these materials gathered. Asking, where did the cloud come from, may be similar to asking where the water in a river came from. Some fell as rain nearby. Some entered from tributaries. Some rose from underground. By the time it reaches a particular point, the river contains a mixture with several histories. The Smith cloud may be a moving mixture rather than one preserved object. Its identity comes from its shared position and motion, not from every atom having left the same place at the same time. This helps explain why different studies can support apparently different ideas without one of them being entirely wrong. The trajectory and sulfur abundance favour a relationship with the outer disk. The large mass and survival problem leave room for accretion, magnetic support, or dark matter. The disturbed tail shows that mixing is active. Its prograde motion suggests that it has inherited angular momentum from the Milky Way, or has been strongly influenced by it. There is another clue in the possibility that the cloud crossed the galactic disk once before. Orbital calculations indicate that its path may have taken it through the disk around 70 million years ago. It is now travelling through the halo and is expected to cross again in roughly 30 million years. If that reconstruction is correct, a cloud made only of unprotected gas would have faced a severe test. The disk is much denser than the halo. Moving through it at high speed would produce shocks, heating, compression, and stripping. Simulations often show ordinary clouds breaking apart during such an encounter. The Smith cloud may not have survived as one unchanged body. The present object could be the remains of a much larger cloud. It could have reassembled or collected new material after crossing. A dark matter halo might have helped it retain gas. Magnetic fields could have reduced mixing along some surfaces. The fact that we can identify it today does not mean it passed through the disk without damage. Its long tail and fragments may be evidence of that damage continuing. There is also uncertainty in the reconstructed orbit. Astronomers know the cloud's present distance and three-dimensional velocity better than they do for most high-velocity clouds, but the Milky Way's gravitational field and gas distribution are not perfectly known. Small changes in the starting measurements or in the galactic model can alter the calculated path over tens of millions of years. The broad picture of a cloud closely connected to the Milky Way is well supported. The exact launch point, mechanism and degree of previous disk interaction remain subjects of research. This is why the Smith cloud can be described both as a solved mystery and an unsolved one. The Hubble measurements strongly reduce the likelihood that it is untouched intergalactic gas. They provided convincing evidence for enrichment by stars and made an outer disk connection plausible. They did not identify the explosion, stellar association, dark subhalo, or sequence of interactions that created the object we observe. The cloud's chemistry tells us where some of its material has been. It does not tell us every event that happened afterward. What we meet today is not a clean specimen from the past. It is an object already being altered by its journey. Gas at the front is compressed. Gas in the tail is stripped and mixed. Ionizing radiation from the Milky Way changes its atoms. The hot corona flows around it. Gravity bends its route. Magnetic fields may be draped across its surface. Every part of the cloud is participating in an ongoing experiment. The Smith cloud is therefore not simply a giant parcel waiting to be delivered. It is a changing boundary between cold gas and a hot galactic environment. Its continued existence tells us something about cooling, turbulence, pressure, and the circulation of matter around galaxies. Its uncertain origin tells us how difficult it is to separate incoming gas from recycled gas once the two begin to mix. Galaxies do not divide their surroundings into tidy categories. Material can leave, collect more material, return, and depart again. An atom created inside a star may be expelled by a supernova, carried into the halo, cooled inside a cloud, and eventually used in another generation of stars. The Smith cloud allows astronomers to see part of this cycle on an unusually large scale. For someone looking at the night sky, none of that motion is visible. The cloud remains absent from the familiar view, and its name remains far less intimidating than its size. Behind that modest name is a structure longer than thousands of neighbouring star systems placed end to end. It contains enough gas to affect future star formation. It carries chemical evidence from older stars and physical scars from its passage through the halo. Whether it began as a galactic outflow, a smaller external cloud, a dark matter-supported traveller, or a mixture of all three processes, it has now become part of the Milky Way's gas cycle. The question of origin cannot be separated from the question of motion. To decide which explanation is physically possible, astronomers must follow the cloud backward and forward through the galaxy's gravitational field. That means examining its speed around the Milky Way, its movement toward the disk, the resistance produced by the halo, and the long curved route that may have carried it away from the galaxy before turning it back again. The Smith cloud is often described as racing toward the Milky Way at roughly 300 kilometers per second. That statement is useful, but it can also create the wrong picture. The cloud is not sitting outside the galaxy and aiming directly at its centre. It is already inside the Milky Way's extended halo, and most of its motion carries it around the galactic centre in the same general direction as the disk rotates. Only part of its velocity is taking it toward the disk. This matters because motion in space has more than one component. A car on a road can move north while also climbing a hill. In the same way, the Smith cloud is moving around the galaxy, inward or outward to some degree, and vertically relative to the disk. Astronomers reconstruct those components by combining its position, distance, radio velocity, and the changing motion seen across its long structure. The result is an oblique path rather than a vertical plunge. It is approaching the disk at an angle while continuing to travel rapidly around the Milky Way. Its speed relative to the galactic centre is close to 300 kilometers per second. That is a little over 1 million kilometers per hour. At that rate, it could cross the diameter of Earth in less than a minute, although Earth would object to being used as a convenient distance marker. Across the galaxy, even this speed produces a slow journey. The Smith Cloud's leading region remains several thousand light-years from the dense central plane. Light crosses that distance in thousands of years. The cloud, moving far more slowly than light, will need roughly 30 million years to reach the disk. This contrast is common in astronomy. An object can move at a speed that would be extreme anywhere near Earth, and still require millions of years to travel between neighbouring regions of a galaxy. The cloud's motion is also not constant in the simple way that a car's cruise control might be constant. Gravity accelerates it. Gas drag slows parts of it. Material is stripped away. The surrounding halo may rotate, reducing or increasing the relative speed depending on direction. When astronomers quote one value for the velocity, they are describing the bulk motion of a complicated object rather than the identical speed of every hydrogen atom. Some gas at the leading edge is compressed. Some in the tail has already slowed. Smaller fragments move at related but distinct velocities. The cloud is travelling as a system, but it is not behaving like a rigid body. There is nothing rigid about it. If a solid object is pushed at one end, forces are transmitted through its material and the entire body responds. In a gas cloud thousands of light years long, pressure waves require time to cross the structure. Different regions can react separately to gravity, heating, and contact with the halo. The word cloud therefore describes a connected pattern in position and velocity, not a single piece with a fixed shape. To understand what is happening to that pattern, we need to look at the region through which it is moving. The Milky Way's visible disk does not mark the edge of the galaxy. Beyond the stars and cold gas lies a much larger halo. Dark matter provides most of the halo's mass, but ordinary matter is present as well. Some of that ordinary matter exists as extremely thin, hot plasma. Hydrogen and helium atoms have been ionized, meaning their electrons have been separated from their nuclei. This hot gas is often called the galactic corona. Its temperature can reach around 1 million degrees, yet its density is so low that the word hot needs a little explanation. Temperature measures the average energy of particles. It does not tell us how many particles are available to transfer that energy. The air inside a hot oven is much less damaging than a metal tray at the same temperature, because the metal contains far more particles in contact with your hand. The galactic corona is thinner than any vacuum humans can easily produce. A spacecraft placed there would not be heated as though it had entered a 1 million degree furnace. There are simply too few particles striking it at any moment. For the Smith cloud, however, those few particles matter. The cloud presents a cross-section thousands of light-years wide and has travelled through the corona for millions of years. Tiny effects accumulate. Every encounter transfers momentum and energy. The halo does not need to be dense to alter an object that is diffuse, extended and exposed for such a long time. An analogy can help, provided we do not ask it to work too hard. A cyclist barely notices still air while standing, but at high speed the air pushes back. The effect becomes stronger as the cyclist moves faster or the air becomes denser. The Smith cloud experiences a related form of pressure as it moves through halo gas. This is ram pressure. The strength of ram pressure depends mainly on the density of the surrounding medium and the square of the relative velocity. Doubling the relative speed increases the pressure by roughly a factor of 4. The phrase relative velocity is essential. If the cloud and the halo gas were moving together at the same speed and in the same direction, there would be little headwind between them. If they moved in opposite directions, the interaction would be much stronger. The Smith cloud follows a prograde orbit. It travels in the same broad direction as the rotating Milky Way. The hot halo may also carry some rotational motion, although probably not as quickly as the disk. Because the cloud is not charging directly against the surrounding flow, its effective headwind may be lower than its full galactic speed suggests. That reduced relative velocity can help it survive longer. It does not remove the pressure. Radio observations show that material at the cloud's edges has shifted toward the velocity of ordinary Milky Way gas. There are also bridges in velocity between the high-speed cloud and slower gas. These features are interpreted as evidence that the edges are being stripped and decelerated. The surrounding medium pulls material away, and the removed gas begins to adopt the motion of its new environment. The cloud's comet-like outline follows naturally from this process. A denser leading body continues forward while loosened material trails behind. The comparison with a comet concerns appearance, not composition. A comet's tail is shaped largely by sunlight and the solar wind. The Smith cloud's tail is shaped by hydrodynamic interaction, gravity, ionization, and probably magnetic fields. It is also much larger. A normal comet tail can extend for millions of kilometers. The Smith cloud's gaseous wake extends for thousands of light years, which makes even an impressive comet look like it has brought a rather small scarf. Ram pressure stripping is not the only process acting at the boundary. Whenever two fluids slide past each other at different speeds, the interface can become unstable. Small ripples grow. The fluids roll together, create vortices, and begin to mix. This is known as the Kelvin-Helmholtz instability. It appears in ocean waves, cloud layers in Earth's atmosphere, planetary atmospheres, and astrophysical gas. Along the Smith cloud's surface, colder cloud material moves beside hotter halo plasma. Their different speeds create shear. Small disturbances can grow into folds and billows, pulling gas from the cloud and mixing it into the corona. The cloud does not need a visible surface for this to happen. The boundary is a gradual change in density and temperature, but it can still support instabilities. Another process, the Rayleigh-Taylor instability, can appear when a denser fluid is accelerated by a lighter one. Fingers and bubbles develop as the fluids rearrange themselves. The exact role of each instability depends on the cloud's density, acceleration, cooling, magnetic field, and geometry. In real galactic gas, several processes operate at once, and none has agreed to wait politely while the others finish. Computer simulations show the result as a turbulent wake. Material is peeled from the outside, broken into clumps, heated and mixed. If that were the entire story, the Smith cloud might disappear rapidly. A diffuse cold cloud moving through hot plasma should be vulnerable, yet observations still reveal a substantial neutral body. Cooling helps. When gas is compressed or mixed, it can radiate energy away. If the cooling is efficient enough, some of the disturbed material can remain relatively cool or even condense. The interface between the cloud and corona is therefore not always a one-way process in which cloud gas is lost. Hot halo gas can mix with cooler, metal-enriched material, radiate energy, and join the cooler phase. In that case, the cloud may lose some atoms while gaining others. This is one reason its present mass does not necessarily equal the mass with which it began its journey. The structure may be continuously exchanging matter with the halo. The balance depends strongly on metallicity, because heavier elements provide efficient ways for gas to radiate energy at certain temperatures. A cloud enriched by previous generations of stars can cool differently from nearly pristine hydrogen and helium. Turbulence increases the area over which mixing occurs. That can accelerate destruction, but it can also promote cooling. The same disturbed boundary may both remove original cloud material and create new cool gas from the surrounding corona. Astronomers sometimes call this condensation or entrainment. The words sound organized. The actual process is a noisy interaction involving shocks, eddies, magnetic fields, and gas changing temperature and ionization state. The Smith cloud's neutral radio body shows only the portion cool enough to retain electrons around hydrogen nuclei. Around that neutral core lies ionized gas. H-alpha observations indicate that the ionized mass is at least comparable to the neutral mass, and maybe several million times the mass of the Sun. The ionized component covers a broader area than the strongest 21 centimeter emission. That makes sense if the outer layers are heated, exposed to ultraviolet radiation, or mixed with the hot halo. The visible radio outline is therefore not the full moving object. It is the colder centre of a wider interaction zone. Some ionization comes from radiation produced by the Milky Way stars. High-energy ultraviolet photons escape from the disk and reach the halo. They can remove electrons from hydrogen in the Smith cloud's outer regions. Collisions also contribute. Gas struck by faster particles can be heated, shocked, and ionized. A shock forms when information cannot move through a medium quickly enough to warn the material ahead. Gas is suddenly compressed and heated as the disturbance passes. Whether a strong shock stands in front of the Smith cloud depends on the cloud speed relative to the local sound speed and on the properties of the hot corona. Because the corona is already extremely hot, its sound speed is high. The cloud's motion may be supersonic in some regions and closer to transonic in others. The interaction is not one smooth bow wave with a simple boundary. Different gas phases experience different effective conditions. Dense, neutral clumps respond more slowly to drag because they contain more mass for a given surface area. Diffuse gas is easier to accelerate and strip. This naturally separates the cloud. The denser core retains more of its original velocity, while lower density material falls behind. Astronomers can see this separation in the broadening and shifting of the hydrogen line near the edges. Gas there spans a wider range of speeds than the central material. The tail acts as a record of deceleration. Not every mark in that record is easy to read. The cloud's three-dimensional orientation changes how projected features appear. Gas that looks adjacent on the sky may be separated along the line of sight. A clump that seems detached could be physically connected by material too faint for a survey to detect. Another clump might be unrelated gas appearing at a similar velocity. Researchers compare maps, spectra, and simulations to distinguish the likely parts of the system. Magnetic fields add another layer. Gas in the halo is ionized, so charged particles respond to magnetic fields. As the Smith cloud moves, field lines can be compressed and draped around its leading surface. This magnetic layer may reduce the direct mixing of particles across parts of the boundary. It can suppress some small instabilities, redirect heat flow, and help organize the wake. Observations of Faraday rotation provide evidence for a magnetic field associated with the cloud's interaction region. Faraday rotation occurs when polarized radio waves pass through magnetized plasma. The plane of polarization turns by an amount that depends on the electron density, magnetic field, and distance through the material. Measurements toward the Smith cloud have suggested fields of several microgauss in parts of the region. That is comparable to magnetic fields found within the Milky Way's disk, though the geometry and exact association remain complex. A magnetic field does not place the cloud inside a protective bubble. It changes the rates and directions of mixing. Some simulations show longer-lived filaments when magnetic fields are included. Others show field lines guiding stripped gas into narrow structures. The outcome depends on the field's strength and orientation. A field parallel to the cloud's motion behaves differently from one crossing the flow. This is one reason no single simple simulation can settle the cloud's history. A realistic model needs gravity, radiative cooling, ionization, turbulence, magnetic fields, the rotating hot halo, the structured disk, and possibly dark matter. It must also cover distances of tens of thousands of light-years while resolving boundaries and clumps that are much smaller. That range is computationally demanding. Increasing resolution reveals new instabilities, and adding more physics changes the result. Simulations are not films of what definitely happened. They're controlled tests of what can happen under specified assumptions. Even with those limits, the models reveal an important principle. The Smith cloud cannot travel through the halo unchanged. It is being eroded now. The word survive needs to be used carefully. A cloud can survive as a recognizable high-velocity structure, while losing most of the atoms it originally contained. Its densest portion can persist after the outer layers disperse. It can also acquire new material and maintain a similar total mass despite continuous replacement. When astronomers say that the Smith cloud may survive until it reaches the disk, they do not mean that every current parcel of gas will arrive together in its present shape. The long tail already proves otherwise. Some of the cloud is joining the Milky Way before the main impact. Stripped material slows, cools, ionizes, and becomes harder to distinguish from the surrounding halo. This is accretion in progress, not a delivery scheduled for one future date. The cloud also carries angular momentum. Because it is moving prograde, gas that joins the disk or halo adds not only mass but rotational motion. That can influence how material settles into the galaxy. If incoming gas had very little angular momentum, it would fall more directly inward. Gas with substantial prograde motion can join the outer disk more gently and remain at larger galactic radii. The Smith cloud moves faster around the galaxy than the disk material beneath its present path. Some analyses place its prograde orbital speed roughly 100 km per second above the local circular rotation. As drag transfers momentum, the cloud can accelerate surrounding gas in its direction of travel, while it slows relative to its original motion. The exchange is spread across a huge volume and a long time. There is no single point where the cloud suddenly hands the Milky Way a package labelled angular momentum. Gravity continues to guide the larger path. The Milky Way's mass pulls the cloud toward the galactic centre and disk. Stars, gas, dark matter and the central bulge all contribute to the gravitational field. A ballistic orbit calculated without drag resembles the trajectory of a thrown object, though on a galactic scale. The cloud rises or falls through the potential while moving around the centre. Gas is not perfectly ballistic because it interacts with its surroundings. Drag changes its velocity, mass loss changes its response, and condensation adds material with different momentum. Still, a ballistic model gives a useful first approximation and produces the broad, boomerang-shaped route often shown in diagrams. Reconstructing that route backwards suggests that the cloud was farther from the disk tens of millions of years ago. Some models place it near or within the outer disk about 70 million years in the past. If it was launched there, its initial upward speed had to overcome the disk's gravitational pull without allowing it to escape the galaxy entirely. Gravity gradually reduced the vertical motion, brought it to a maximum height, and began pulling it back. At the same time, the cloud continued orbiting around the Milky Way. This means its return point is not the same as its launch point. During 70 million years, both the cloud and the disk rotate. A parcel thrown upward from one region does not hover above that location, while the galaxy turns beneath it. By the time it returns, it may meet the disk thousands of light years farther along the orbit. This makes the word boomerang slightly deceptive. The Smith cloud does not travel out and return to the hand that threw it. It follows a curved galactic trajectory and intersects the disk in a different place. The alternative is that the cloud began farther out in the halo and is approaching the disk for the first time. In that case, its prograde motion and chemical enrichment require a different history, perhaps involving interaction with material lost by the Milky Way. Both possibilities must explain its current speed. Gravity alone can accelerate an infalling cloud, but drag removes kinetic energy. A massive, dense object retains speed more effectively than a light, diffuse one. The Smith cloud's large total gas mass helps it resist deceleration, while its broad surface makes it vulnerable. The resulting balance is visible across the structure. A fast central body surrounded by slower stripped material. Its current kinetic energy is enormous. Moving several million solar masses at hundreds of kilometers per second requires more energy than a small number of supernovae could provide. This is one challenge for launch models. A substantial star-forming region with many massive stars may be needed, or the cloud may have gained mass after launch so that less material originally required acceleration. It is also possible that gravity supplied much of the present speed during the return journey. The energy budget depends on what the cloud's mass was at each stage, which material belongs to the original outflow, and how much halo gas is condensed into it. That uncertainty prevents a simple backward calculation. A person watching one frame of a fountain cannot determine exactly how much water left the nozzle if rain has fallen into the stream, wind has removed droplets, and the pump pressure has changed. The Smith cloud offers astronomers one frame, along with velocity and chemical clues. The rest must be reconstructed. Its passage through the halo is useful precisely because the damage contains information. The amount of stripping constrains the halo's density. The shape of the head and tail tests models of the relative motion. Ionized emission reveals heating and radiation. Magnetic measurements probe fields at the disk-halo boundary. In this sense, the cloud acts as a moving experiment through a region that is otherwise difficult to study. The Milky Way's hot corona is faint because its particles are widely separated. Detecting it directly is challenging. A cold cloud travelling through it makes the invisible medium easier to notice, much as wind becomes visible when it pushes leaves across a road. The leaves tell us about the air. The Smith cloud's tail tells us about the halo. Its continued neutral hydrogen also tells us that cooling and shielding are effective in at least some regions. Dense clumps can block part of the ionizing radiation. Their interiors remain cooler while their outer surfaces are heated. As gas is compressed at the front, its density rises and cooling can become more efficient. The leading edge may therefore be both the most heavily pressured and one of the best places for neutral material to persist. Farther back, lower density gas is easier to ionize and mix. This contributes to the broad ionized envelope in the fragmented radio tail. The cloud is likely becoming less coherent as it approaches denser galactic gas. Ram pressure grows as the ambient density increases. The outer halo is exceptionally thin, but the disk-halo interface contains more material. Each stage of the descent becomes more difficult. Observations and simulations suggest that the cloud will be stretched and disrupted before all of its gas reaches the densest parts of the disk as one intact body. That does not prevent its mass from reaching the Milky Way. Destruction of the cloud means redistribution of the gas, not disappearance of matter. Hydrogen stripped from the main body remains hydrogen. It may spread out, heat, cool again, and join the galactic environment over a larger area. The future encounter will therefore begin gradually rather than on one exact morning 30 million years from now. It has already begun in the halo. Gas bridges, slower fragments, ionized emission, and the comet-like tail show that the Smith cloud is transferring material and momentum to the Milky Way today, as measured from the delayed signals reaching us. The denser body continues forward because its inertia carries it through the surrounding plasma. Gravity pulls it toward the disk. Drag works against the relative motion. Cooling rebuilds some cool gas. Turbulence tears other parts away. Magnetic fields guide charged particles around the boundary. Ultraviolet light changes the ionization state. Every process alters the next. The result is not a quiet object travelling through empty space. It is a large-scale collision that has been unfolding for millions of years at densities too low for human senses to detect. If we could accelerate the view, the cloud would not resemble a solid projectile. Its front would compress and deform. Filaments would peel backward. Clumps would appear, fade, and merge. A wider envelope of ionized material would surround the bright radio core. The tail would lengthen as the whole structure followed its curved orbit toward the disk. That curve is the next part of the mystery, because following it backward produces the possibility of a previous departure from the Milky Way, while following it forward places the cloud on a return route toward the outer galactic disk. This is where the Smith cloud gained its familiar description as a galactic boomerang. The phrase gives us an immediate picture. Something leaves, travels through the air, follows a curved path and comes back. It is a useful starting point, although the real motion is much slower, much larger, and considerably less convenient to practice in a public park. The cloud's reconstructed journey lasts around 100 million years. According to the widely presented model, it left a region near the outer edge of the Milky Way stellar disk about 70 million years ago. It is currently several thousand light-years below the galactic plane and is expected to cross the disk again in roughly 27 to 30 million years. Its chemical composition supports a connection to the outer Milky Way, where the gas contains fewer heavy elements than gas closer to the galactic centre, but far more than untouched material from intergalactic space. Calling this motion a return home does not mean the cloud is heading toward the precise location where it began. The Milky Way rotates, and so does the cloud. During the tens of millions of years required for the journey, the disk moves through a substantial part of its orbit around the galactic centre. If the gas was launched from one spiral arm, that region did not remain patiently underneath it. Stars and gas continued moving around the galaxy. Spiral structure also evolved, and the cloud followed its own path through the halo. The Smith cloud's next disk crossing will therefore take place far from its possible launch point. It is coming home in the broad sense that its gas is returning to the Milky Way's main disk, not in the sense that it has remembered a particular address. The word boomerang also suggests that the cloud was thrown outward in one clean event. That may be true in a general sense, but astronomers do not know what provided the push. A large amount of gas does not leave a galactic disk without a reason. Gravity pulls material toward the disk and the galactic centre. Gas that rises into the halo must first receive enough energy and momentum to move against that pull. The Smith cloud's present gaseous mass is at least several million times the mass of the Sun when its neutral and ionized components are considered together. Accelerating that much material requires an enormous energy source. One possible source is a group of massive stars. Massive stars affect their surroundings long before they explode. They release strong ultraviolet radiation and drive powerful stellar winds. Those winds push into nearby gas, creating expanding cavities. When several massive stars form in the same region, their combined winds can produce a superbubble. The hot interior expands while a shell of cooler gas gathers around the edge. The most massive stars then begin ending their lives as supernovae. Each explosion adds energy to the bubble. If enough explosions occur close together, the superbubble can grow until it breaks through the thinner upper or lower surface of the galactic disk. Hot gas then escapes into the halo. Cooler fragments from the shell may be pushed along with it. This kind of process is observed or inferred in many galaxies. Star-forming disks frequently show hot gas rising above them, and galaxies with especially intense star formation can produce outflows extending thousands of light years. The Milky Way is quieter than a powerful starburst galaxy, but it still contains regions where clustered supernovae can create large chimneys and fountains. A galactic fountain does not need to remove material forever. Some gas rises, loses speed, cools, and returns under gravity. The name fountain describes the overall circulation. Gas moves from the disk into the halo and later comes down again, sometimes after mixing with material that was already in the corona. The Smith cloud's enriched sulfur abundance made this explanation especially attractive. It contains material that has been processed by stars, and its composition resembles gas in the outer disk. A fountain could place such material in the halo without requiring it to have arrived from another galaxy. The details are not easy. A simple vertical launch from the disk can reproduce parts of the Smith cloud's present position and velocity, but it has difficulty explaining the direction of the long comet-like tail. If the tail is produced by ram pressure, it should extend broadly opposite the cloud's motion relative to the surrounding halo gas. In some straightforward fountain models, the calculated direction does not match the observed morphology. Researchers have tested ways to correct that disagreement. The original outflow may have been inclined by more than 40 degrees rather than launched straight up. Another possibility is that a very fast wind from a superbubble continued accelerating the cloud after it entered the halo. Models using such a wind require speeds around 1,000 km per second or more, depending on the assumed density. Those speeds are high, but winds associated with energetic star-forming regions can reach comparable values. A fast wind would not need to carry the entire Smith cloud at its present mass from the beginning. The object may have grown during its journey. As cool, enriched gas travels through the Milky Way's corona, it creates a turbulent wake. Hot coronal gas mixes with cooler material, loses energy through radiation, and may condense into the wake. The cloud can therefore collect some of the halo as it moves. This possibility changes the energy calculation. If the Smith cloud was smaller when it left the disk, the launch event did not need to accelerate its entire present mass. Some of the gas could have joined later. The cloud we see would then be partly returning disk material and partly cooled halo material travelling with it. Such an object is still a galactic boomerang, although it has picked up additional passengers along the route. The cloud's rotation around the Milky Way provides another clue. It follows a prograde path, meaning it moves in the same general direction as the galactic disk. That is what we would expect from gas launched from the Milky Way. Material beginning in the disk already shares the disk's rotational momentum. Throwing it upward does not erase its sideways motion. Imagine standing on a moving train and tossing a ball straight upward. The ball does not land several carriages behind you. It continues moving forward with the train while it rises and falls. The Smith cloud's case is more complicated because the galaxy does not move as one rigid platform, and because the cloud spends millions of years interacting with the halo. The principle remains useful. Gas launched from a rotating disk continues orbiting the galactic centre while it travels vertically. The Smith cloud is not moving at exactly the same rate as the disk beneath it. Its prograde orbital motion appears to be roughly 100 km per second, faster than the local galactic rotation in some reconstructions. This unusual speed is one of the reasons a simple fountain origin remains debated. A launch from the disk must explain where that extra motion came from. An inclined ejection or a fast superbubble wind could add momentum. Interaction with a rotating corona could also change the velocity, although drag generally reduces differences rather than creating a very fast prograde orbit. An alternative possibility is that the cloud did not leave the disk in its current form. It may have approached the Milky Way inside a small dark matter halo, passed through the disk, captured enriched gas, and emerged on the other side. In that scenario, the boomerang description still applies to the visible gas, but the object's history is different. Instead of ordinary disk gas being thrown out by stars, an invisible mass concentration may have carried gas through the galaxy. Dark matter would help solve the survival problem. Its gravity could hold the gas together while it crossed the dense disk and moved through the hot corona. Simulations have shown that an unprotected gas cloud may be severely disrupted during a high-speed disk crossing. A cloud inside a dark matter sub-halo can retain more material, especially when radiative cooling is included at sufficiently high numerical resolution. This does not mean astronomers have detected a dark matter halo around the Smith cloud. They have not. The dark matter proposal is a model designed to explain difficult features. It provides gravitational confinement without producing visible stars, but it must also agree with the cloud's chemical composition, motion, shape, and lack of an obvious compact centre. The sulfur abundance shows that much of the observed gas has been enriched by stars. A dark subhalo arriving from outside the Milky Way would therefore need to collect galactic gas during or after a disk passage. That possibility is physically interesting, but it requires more steps than a basic fountain model. Neither explanation is entirely comfortable. The fountain model naturally explains why the gas resembles the outer Milky Way chemically, and why it moves in the prograde direction. It struggles with the required energy, the cloud's present mass, its unusually rapid rotation, and the survival of a large coherent structure. The dark matter model helps with survival, and may explain a previous disk transit. It lacks direct evidence for the proposed dark halo, and must account for how enriched galactic gas became attached to it. The popular illustration of the Smith cloud leaving the outer disk 70 million years ago and returning 30 million years from now therefore represents one well-supported interpretation, not a recording of an event astronomers watched happen. The model combines the cloud's present position, velocity, metallicity, and the Milky Way's gravitational field. It then calculates a path consistent with those measurements. Every part of that calculation contains uncertainties, The cloud's distance is well constrained compared with most high-velocity clouds, but it still has an uncertainty. Its velocity varies across the structure. The galactic gravitational field depends on the distribution of stars, gas, and dark matter, which is measured through models rather than known perfectly. The hot corona adds drag, but its density and rotation are not uniform. The cloud loses gas and may gain gas. These changes alter the path. Following the orbit backward for 70 million years magnifies small differences in the starting conditions. Two reasonable models can agree about the cloud's current position, while giving different earlier trajectories. There is even disagreement over whether it is currently descending or still rising in particular fountain calculations. The simple boomerang picture places the cloud on the returning section of its orbit. Some detailed fountain models that include drag and condensation reproduce its current measurements while placing it in an ascending phase. That difference does not mean one group forgot which direction the Milky Way was. It reflects different assumptions about the cloud's orientation, the halo flow, and how its observed velocity is translated into a model trajectory. The safest conclusion is that the Smith cloud has a strong physical connection to the Milky Way and is moving toward a future encounter with the disk. Its precise route into its present position remains under investigation. The boomerang label remains useful because it captures the leading chemical interpretation. Material associated with the Milky Way is now approaching the Milky Way again. It should not be mistaken for proof that the cloud left from one known point, followed one clean arc, reached a tidy maximum height, and is now returning unchanged. Gas does not travel like a carefully manufactured wooden object. The Smith cloud has been distorted, its tail has been stripped, its ionized envelope has spread. It may have collected coronal gas and lost some of its original material. If it began near the outer disk, the object returning is not chemically or physically identical to the object that left. This is normal for galactic recycling. Matter moves between different environments and changes along the way. Gas expelled by supernovae can cool in the halo. Halo gas can condense into the returning flow. Dust grains may be damaged or formed. Atoms can become ionized and later regain electrons. The identity of the cloud belongs to the moving structure, not to an unchanging membership list. Its position near the outer Milky Way is significant. The Sun lies roughly 26,000 light-years from the galactic center. The Smith cloud's chemical composition is consistent with material from a region around 40,000 light-years from the center, well beyond the Sun's orbit. The outer disk contains fewer stars and lower average metallicity than the inner galaxy. Its gravitational pull is weaker, and gas may be easier to lift into the halo there than close to the center. A superbubble in that region could break through the disk more readily, because the overlying gas layer is thinner. At the same time, the lower rate of star formation makes it less obvious where enough massive stars would have gathered to produce the required energy. A major stellar association could have existed 70 million years ago and dispersed since then, but there is no confirmed surviving source that can be identified as the launch site. The event may have involved a chain of supernovae rather than one explosion. It may have been connected to a spiral arm region where gas became compressed and formed a large group of stars. Another object could have disturbed the disk. A small satellite galaxy, dark matter subhalo, or fast-moving gas cloud might have passed through, pushing material out. The Milky Way has interacted repeatedly with smaller companions. The disk is not isolated from its surroundings, and disturbances can produce waves, warps, holes, and vertical motions. No specific culprit has been confirmed for the Smith cloud. The launch occurred too long ago for the scene to remain intact. Massive stars responsible for a superbubble would have died. The remaining stars would have drifted. Gas clouds would have changed shape, and galactic rotation would have carried everything away from its earlier position. Astronomers are attempting to solve a 70-million-year-old event using one damaged object and the chemical traces it carries. This is similar to reconstructing an accident after the road has been resurfaced, the vehicles have been dismantled, and the witnesses have completed a substantial fraction of an orbit around the galaxy. The future path is easier to estimate because it covers less time and begins with measurements we have now. The leading part of the Smith cloud sits about 2.9 kiloparsecs, or roughly 9,500 light-years, from the galactic plane. Its measured three-dimensional speed is close to 296 kilometers per second. Models place its disk crossing approximately 27 million years in the future. The crossing point is expected to lie in the outer Milky Way, far from the solar system. Earth is not in the cloud's path, and the gas is not a solid projectile capable of travelling through the galaxy while flattening planets. By the time the main body reaches the disk, much of it will probably have fragmented. Some material is already being stripped, and the rising ambient density will intensify the interaction. The term impact can therefore sound more sudden than the event will be. There may be shocks, compression, heating, turbulence, and large-scale disturbances in the local interstellar gas. The process will unfold across thousands or millions of years rather than during one afternoon. Gas arriving before the densest core will begin changing the disk environment. Fragments will cross at different times and locations. The remaining body may spread as it encounters denser material. Even if the cloud retains a strong central concentration, there will not be a single instant when the entire object arrives. Its entry resembles an extended weather system reaching a coastline more than a stone striking the ground, provided the weather system is thousands of light-years long and the coastline is made of interstellar hydrogen. The phrase "coming home" also deserves one more adjustment. The Milky Way's halo is already part of the galaxy. The Smith cloud has not been outside the galactic system during the period we observe. It remains gravitationally bound and travels through matter associated with the Milky Way. Its return is specifically a return to the dense star-forming disk. The halo and disk are not separate objects. They are connected regions of one galaxy, exchanging matter continuously. Gas can rise from the disk, mix with the corona and fall back. Other gas may enter the halo from satellite galaxies or the intergalactic medium before eventually settling into the disk. The Smith cloud stands out because it is unusually massive and because its trajectory can be estimated. It is a visible example in radio wavelengths of a process that may occur in smaller and less easily measured forms all around the Milky Way. The galactic fountain is not one fountain. It is a collection of outflows, cooling regions, falling clouds, and turbulent interfaces spread across the disk. Some are driven by individual stellar groups. Others may be connected to the activity near the galactic centre. Some gas may circulate only a short distance above the plane, while other material reaches far into the halo. The Smith cloud may represent an especially energetic version of this recycling process. Its journey shows why a galaxy should not be imagined as a fixed collection of stars. The disk breathes gas into the halo and receives gas in return. That exchange helps regulate star formation. Outflows remove heat and heavy elements from crowded regions. Returning clouds provide cooler material and may trigger compression when they meet the disk. The cycle also spreads elements created by stars. Oxygen, sulfur, carbon, and other atoms can be carried away from their birthplace and later deposited in another region. If the Smith cloud began in the outer disk, it has carried enriched material thousands of light-years into the halo. During its travels, it may have mixed that material with the hot corona. When it returns, the mixture could enter a different part of the disk and eventually contribute to stars that have no direct connection to the stellar population that launched it. The atoms do not keep a record that future astronomers can read easily. Their history becomes part of the chemical mixture of the galaxy. The Smith cloud's journey is long by human standards, but ordinary compared with the age of the Milky Way. 70 million years ago, non-avian dinosaurs still lived on Earth. The cloud may already have been well into its halo excursion, while animals moved through forests and coastal plains below our sun. 27 million years from now, Earth's continents will occupy different positions, and the species living here may be very different from those alive today. The cloud will continue following its orbit regardless of those changes. This does not make its journey mysterious in a supernatural sense. It simply places it outside the timescales our daily intuition handles well. The equations of motion remain the same. Gravity, drag, cooling, and pressure work continuously. The difficulty lies in measuring every relevant condition across millions of years. Astronomers describe the cloud's path through probabilities and models rather than certainty. The boomerang story is supported by its enriched chemistry and close relationship with the Milky Way, but the launch mechanism and exact orbit remain open. The lack of a complete answer makes the object more useful, not less. A theory that explains the cloud must account for several facts at once. It must produce its large mass, its prograde motion, its distance from the disk, its comet-like form, its metallicity, and its continued existence. Explaining one feature while ignoring the others is not enough. A powerful superbubble may launch enriched gas, but must provide the correct direction and energy. A dark matter halo may protect the cloud, but must explain its galactic chemical signature. Fresh accretion may supply mass, but does not naturally produce its observed abundance of sulfur. The cloud behaves like a test placed in the path of every proposed model of gas circulation. For now, the most careful description is that the Smith cloud appears to contain recycled or heavily contaminated galactic material and is moving toward the Milky Way's outer disk. It may have been ejected through a fountain-like process, though other scenarios involving a previous disk crossing or dark matter remain under study. Its route resembles a boomerang when drawn across a diagram of the galaxy, but the line on that diagram hides almost everything happening to the gas. It hides the stripping at the edges, the condensation in the wake, the pressure on the leading surface, the changing ionization, and the possibility that much of the cloud's material has been replaced during its journey. A path can be drawn with one smooth curve. The object following it is anything but smooth. As the Smith cloud moves closer to denser regions of the Milky Way, the forces trying to break it apart will grow stronger. If it truly left the disk once before, it has already endured conditions that should have severely damaged an ordinary gas cloud. At first, the survival problem seems simple. The Smith cloud is large and massive, so perhaps it continues moving because large things are difficult to stop. That is partly true. A dense object has more inertia than a thin one, and the cloud's most concentrated regions can resist the surrounding flow better than its diffuse edges. Mass alone does not solve the problem. The Smith cloud is made of gas rather than solid material. Its atoms are not locked into a rigid structure. Different parts can be pushed, heated, slowed, or stripped away independently. The cloud is crossing a hot galactic environment at high speed, and calculations show that an unprotected gas cloud can lose its identity long before completing such a journey. The fact that we still observe a large neutral structure does not mean it has remained unchanged. It may instead mean that destruction is occurring more slowly than expected, that some of the lost material is being replaced, or that an unseen force is helping the gas remain concentrated. Astronomers refer to several characteristic times when studying a cloud moving through a surrounding medium. One of the most useful is sometimes called the cloud-crushing time. The name sounds more violent than most astronomical terminology, although in this case it is reasonably accurate. When fast-moving external gas strikes a denser cloud, a shock travels into it. The front is compressed while pressure differences begin disrupting the structure. The cloud-crushing time estimates how long that internal shock needs to cross the cloud. It depends on the cloud's size, the contrast between its density and the surrounding medium, and their relative speed. A larger or denser cloud takes longer to crush. A faster external flow shortens the time. After several cloud-crushing times, a simple unmagnetized and non-cooling cloud in a simulation is often severely fragmented. Instabilities grow at the surface, material is stripped into a wake, and the original central body becomes difficult to identify. For a small, high-velocity cloud, this may happen over a few million years. The Smith cloud's journey through the halo appears to have lasted far longer than that. Something in the basic picture is therefore incomplete. One helpful feature is the cloud's prograde orbit. It moves around the Milky Way in the same direction as the galactic disk and probably in the same broad direction as at least some of the hot halo's rotation. The surrounding gas is not stationary while the cloud rushes through it. If both are moving in related directions, the speed between them is lower than the Smith cloud's full orbital velocity around the galaxy. Ram pressure depends strongly on that relative speed. A smaller headwind produces less stripping and reduces the rate at which momentum is transferred from the cloud to the halo. Imagine two cars travelling side by side at similar speeds. Each may be moving quickly relative to the road, but neither experiences the other as racing past. If one car slows, their relative motion increases. The Smith cloud and the corona are not moving as neatly as cars on parallel lanes. The halo's rotation is slower and less organised than the disks, and the cloud also has vertical and radial motion. Still, its prograde path is gentler than a direct collision with gas moving the opposite way. That advantage helps, but it does not make the journey safe. The Smith cloud's radio shape shows clear damage. Its neutral hydrogen is concentrated toward the front, while filaments and fragments extend behind it. Gas at the edges has been decelerated toward velocities associated with the Milky Way. The object is surviving in the sense that a recognizable core remains. It is not surviving in the sense that every original atom is traveling together. The cloud's internal density is probably uneven. Radio maps show compact concentrations within the larger structure, and denser clumps respond differently from diffuse gas. A dense clump contains more mass relative to the area exposed to the incoming flow. It is therefore harder to accelerate and strip. Its outer layers may be removed while the center continues moving. The same clump can also shield its interior from ionizing radiation. High-energy photons from the Milky Way strike the surface first. If the hydrogen column is thick enough, many photons are absorbed before reaching the center, allowing some gas to remain neutral. This creates a layered structure. The interior can be cooler and mostly neutral. The outside may be warmer and partly ionized. Beyond that lies a turbulent interface where cloud material mixes with the hot corona. The layers are not smooth or permanent. They shift as the cloud deforms, but they help explain how neutral hydrogen can remain detectable inside an object surrounded by million-degree plasma. Cooling is another important part of the answer. Gas heats when it is compressed, shocked, or mixed. Heating raises the speed of its particles and can cause a cloud to expand. Expansion lowers the density, making the gas easier to strip. If the gas can radiate that energy away, the sequence changes. Cooling allows compressed material to remain dense. Dense gas has stronger self-shielding and resists acceleration more effectively. Heavy elements make radiative cooling more efficient across many temperatures. The Smith cloud contains sulfur and other products of stellar processing, so it does not behave like pure hydrogen and helium. Atoms and ions of carbon, oxygen, silicon, sulfur, and other elements have many possible energy transitions. Collisions can excite them, and they later release photons. Those photons carry energy away from the gas. Dust may contribute to the thermal behavior as well, although grains can be damaged by shocks and hot plasma. Cooling does not simply freeze the cloud into a stable block. It competes with heating. At the leading edge, compression and shocks add energy. In the wake, turbulent mixing creates gas at intermediate temperatures. Ultraviolet radiation continues ionizing exposed regions. Whether a parcel cools depends on its density, composition, and the amount of time available. A dense mixed region can radiate rapidly and become part of the cooler cloud. A thin region may remain hot and disperse into the corona. This leads to a result that initially seems strange. Mixing can help a cloud survive. Mixing is usually described as destructive because it blends cold cloud material with hot halo gas. If the mixture remains hot, the cloud loses mass. Under the right conditions, however, the mixed gas has a temperature and density that allow it to cool efficiently. Hot coronal material then condenses into the wake. the cloud loses some of its original atoms but gains new atoms from its surroundings. Its cold gas mass may remain stable or even grow while its membership changes. A useful comparison would be a snowball rolling across wet snow. Pieces break off, but new snow sticks to it. The final snowball may have a similar size even though much of the original material has been replaced. The Smith cloud is not rolling across anything, and the galactic corona is not snow, but the exchange of material is similar. This idea changes what survival means. Perhaps the Smith cloud has not carried one uninterrupted parcel of gas from its starting point. Perhaps it has maintained a moving region of cool, high-velocity material through a balance of stripping and condensation. The head may contain a greater fraction of the original dense gas. The wake may contain a larger mixture of stripped cloud material and cooled halo gas. Chemical measurements support the possibility of mixing because different sightlines do not always produce identical abundances. The cloud's composition may vary between its central body and its disturbed tail. That variation makes it difficult to use one metallicity value as a complete record of origin, but it provides evidence that the cloud has exchanged matter with its surroundings. Computer models are essential for studying this process, because no human observation can follow the cloud for millions of years. Researchers create a numerical cloud, place it inside a model galactic halo, assign temperatures, densities, velocities, and chemical properties, and calculate how the system changes. The calculation divides space into cells or particles. At each time step, the computer solves approximations to the equations governing gas flow, gravity, cooling, and sometimes magnetic fields. The outcome depends strongly on resolution. If the simulated cells are too large, small clumps and thin mixing layers disappear. The cloud may look smoother and behave differently from real gas. Instabilities may grow too slowly, or artificial numerical mixing may destroy the cloud too quickly. Increasing the resolution reveals more structure. Dense knots form, narrow filaments develop, and cooling can operate inside regions that a coarse model would average away. This creates an awkward situation. A low-resolution simulation may show complete destruction, while a higher-resolution version of the same scenario preserves or reforms more cold gas. Neither result should be accepted without examining the numerical limits. Researchers testing the Smith cloud have found that radiative cooling and spatial resolution on scales of roughly 10 parsecs or better can be critical when modelling a possible passage through the galactic disk. A parsec is more than 3 light-years, so 10 parsecs is still large by human standards. For a simulation covering tens of thousands of light-years, however, resolving every 10 parsec region requires enormous computing power. Even high-resolution simulations simplify the real environment. The Milky Way's halo is not perfectly smooth. The cloud is not an ideal sphere. The disk contains spiral structure, molecular clouds, cavities, magnetic fields, and gas at many temperatures. The initial conditions are uncertain because astronomers observe only the cloud's current state. A simulation can show that one proposed history is possible or unlikely. It cannot prove that nature selected that exact version. Among the proposed survival mechanisms, dark matter provides the strongest form of unseen support. A cloud made only of gas is held together by its own gravity, external pressure, and internal dynamics. The Smith cloud's gas is massive, but it is spread across such a large volume that its self-gravity may not be enough to maintain a compact object through the entire journey. If the cloud sits inside a dark matter subhalo, the gravitational field would be much stronger than the visible gas alone suggests. Dark matter would not block hot particles like a physical shield. Instead, its gravity would pull dispersed gas back toward the center and reduce the rate at which the cloud expands. Expansion is dangerous because it increases the exposed surface area and lowers the density. A confined cloud remains smaller and more resistant to ram pressure. Early models proposed dark matter halos with masses far exceeding the gaseous mass of the Smith cloud. Such an object could resemble a small galaxy that failed to form many stars. The The Milky Way's main halo is expected to contain many smaller dark matter concentrations left from the hierarchical growth of the galaxy. Some may have retained gas, while others lost it through radiation, ram pressure, or earlier interactions. Placing the Smith cloud inside one of these subhalos could explain why it survived a long fall through the corona, and perhaps even a previous crossing of the disk. Simulations have shown that a sufficiently massive and concentrated dark matter halo can improve survival dramatically. In some calculations, gas clouds without dark matter reach the disk but are destroyed during the crossing, while dark matter-confined versions retain or later reacquire a substantial amount of gas. The disk crossing remains severe even with dark matter. As the cloud enters dense galactic gas, shocks move through it. The gaseous component can be torn away from the dark halo, leaving the invisible concentration to continue along the orbit. Later, the dark halo might collect new gas from the disrupted material or from the surrounding environment. In that model, the Smith cloud seen today may not be the gas that originally entered the disk. It may be a streamer or reaccreted structure associated with a dark subhalo that has already moved ahead. Other magnetohydrodynamic simulations have produced even harsher outcomes. They show the gas being completely dispersed during a disk collision while the dark halo passes through. The halo can then accrete a smaller amount of material on the far side. These results illustrate why dark matter is not a simple answer. It can provide gravity, but the gas and dark matter do not have to remain aligned. Gas feels pressure and shocks. Dark matter, as normally modelled, passes through ordinary gas with little direct interaction. A disk crossing can separate them. If a dark halo currently leads the visible cloud, astronomers would need to determine where it should be and search for indirect effects. No confirmed dark matter centre has been identified. The Smith cloud also contains enriched galactic material, which complicates the idea that it is a nearly pristine failed galaxy. A dark subhalo could have collected that material during a passage through the Milky Way, but this adds another stage to the history. Dark matter remains a plausible aid to survival rather than an established component. Magnetic fields offer a different kind of support. The galactic halo contains magnetized plasma. As a conducting cloud moves through that plasma, field lines can be swept up, compressed, and bent around the leading surface. This process is called magnetic draping. Picture water flowing around the front of a stone. The flow lines separate, move around the sides, and become compressed near the obstacle. Magnetic field lines in a plasma can develop a related arrangement around a moving gas cloud. The accumulated field creates magnetic pressure and tension. It can reduce direct mixing across parts of the boundary, suppress some small-scale instabilities, and alter how stripped gas enters the wake. This does not produce an airtight magnetic shell. Charged particles can still move, reconnection can change the field geometry, and instabilities can grow, along directions the field does not strongly resist. The field may nevertheless extend the cloud's lifetime and help preserve filaments. Astronomers detected evidence for magnetized gas associated with the Smith cloud through Faraday rotation. Radio waves from distant background sources are often polarized. When those waves pass through ionized gas containing a magnetic field, their plane of polarization rotates. The amount of rotation depends on the number of free electrons, the strength of the magnetic field along the line of sight, and the distance traveled through the plasma. By comparing many background sources seen through and around the Smith cloud, researchers can map changes associated with its ionized gas. Early measurements found enhanced rotation near a decelerated filament and inferred a line-of-sight magnetic field component of at least several microgauss in that region. A later survey used more than 1,000 background radio sources. The pattern indicated that a field is draped over the ionized cloud and compressed near its head. The estimated peak line-of-sight component was greater than about 5 microgauss. A microgauss is 1/1,000,000th of a gauss. That sounds extremely weak, and it would be weak compared with the magnetic field near an ordinary household magnet. Across interstellar distances and very low gas densities, however, a few microgauss can be dynamically important. The magnetic energy need not dominate every part of the cloud to influence the boundary where stripping occurs. The observations do not prove that the field has protected the Smith cloud for its entire history. The measured field may have been amplified recently by compression. It could belong partly to the surrounding Milky Way gas rather than to the cloud's original material. A draped field also works best against disturbances that bend field lines in particular directions. Other modes of disruption can continue. Magnetism is therefore another piece of the answer, not the complete answer. External pressure can contribute as well. A cool gas cloud tends to expand unless internal gravity or outside pressure contains it. The hot corona, though thin, applies thermal pressure to the cloud's surface. The cloud can settle into approximate pressure balance, with its cooler gas having a higher density than the hot surroundings. At the leading edge, ram pressure adds to that confinement. The gas is compressed rather than allowed to expand freely. Compression can raise the cooling rate because particles collide more often at higher density. The leading region may therefore be maintained by a combination of external pressure and radiative cooling, even while material is stripped from the sides. This gives the Smith cloud a constantly changing form. The front is compressed, the edges are unstable, the tail contains mixed and decelerated gas. Dense clumps survive longer than diffuse layers. A person seeing only one radio image might interpret the outline as the permanent shape of an object. It is better understood as the current arrangement produced by competing processes. The cloud may also have started much larger. An object can lose 90% of its mass and still leave an impressive remnant if the initial mass was enormous. Models in which the Smith cloud travelled through the halo or crossed the disk often require a progenitor many times more massive than the present neutral cloud. Material removed during the journey would now be spread across the halo or incorporated into the Milky Way. The current head and tail would be the portion that remains coherent enough to identify. This possibility reduces the need for perfect protection. The cloud does not have to survive intact. It only has to leave a surviving or regenerated component resembling the object we observe. The difficulty is that a more massive progenitor requires an explanation of its own. A galactic fountain must lift more gas. An infalling object must begin with a larger supply. A dark halo must hold enough baryonic matter before entering the Milky Way. Every solution moves part of the problem rather than removing it. The cloud's changing ionization state further complicates estimates of survival. Neutral hydrogen produces the 21 centimeter maps used to define the cloud, but ionized hydrogen may contain at least as much mass. If neutral gas becomes ionized, it disappears from the radio map without leaving the physical region. An observer might conclude that the cloud has lost material when some of it has merely changed into a form measured by different instruments. Ionized gas can later cool and recombine, returning to the neutral state. The visible radio cloud can shrink or grow even if the total amount of hydrogen changes less dramatically. Astronomers therefore combine radio data with hydrogen alpha emission, ultraviolet absorption, and models of the radiation field. Each method detects different temperatures and ionization stages. No single instrument sees the full cloud. A similar problem affects the tail. Some fragments may appear disconnected because the material between them has become too ionized or too diffuse for 21 centimeter surveys. The structure could be more continuous than the radio image suggests. Conversely, gas that appears connected in projection may occupy a different distance. Velocity information helps, but the three-dimensional arrangement remains uncertain. The most realistic answer to the survival question is therefore a combination of several effects. The Smith cloud is unusually massive. Its denser clumps resist drag longer than diffuse material. Its prograde orbit reduces the relative wind. External pressure compresses the front. Radiative cooling prevents some heated gas from expanding. Turbulent mixing may condense fresh halo material into the wake. Magnetic draping reduces disruption along parts of the surface. A dark matter halo may provide additional gravity, although direct evidence remains absent. The cloud may also be the remnant of a much larger object rather than a fully preserved traveller. None of these mechanisms requires the Smith cloud to remain unchanged. In fact, all observations suggest change. The head-tail shape, decelerated filaments, ionized envelope, chemical mixing, and fragmented radio structure are signs of ongoing disruption. The apparent contradiction disappears when survival is defined more carefully. The Smith cloud survives as a recognizable concentration of gas moving together at high velocity. It does not survive as a sealed container carrying the same contents through space. That distinction applies to many objects in astronomy. A storm remains identifiable even while air and water flow through it. A flame retains a shape even though the molecules within it are constantly replaced. The Smith cloud may be a similarly persistent process. Gravity, pressure, cooling, and motion create a travelling region in which gas can remain cooler and denser than the halo. Material enters and leaves, yet the large-scale structure continues. This view may explain why asking whether the cloud will survive until impact does not have a simple yes or no answer. Some of its gas is already being delivered to the Milky Way. Some will disperse before reaching the disk. Dense fragments may penetrate farther. Other material may cool in the wake and follow later. A proposed dark halo could cross the disk even if most of the gas does not. The radio-defined cloud might disappear while its hydrogen continues joining the galaxy in smaller pieces. By the time the Smith cloud reaches the dense disk environment, it will probably look different from the object map today. Its leading region will encounter stronger ram pressure. Shocks will become more powerful. Neutral gas will be compressed and ionized. The tail will continue depositing material behind it. The encounter may produce holes, shells, or disturbed regions in the outer galactic gas, depending on how much mass remains concentrated. If dark matter is present, the invisible component may continue through while gas lags behind. If no dark halo exists, the cloud may spread across a broad region and merge more directly with the disk. The survival mystery is therefore connected to the next event. How much of the cloud remains together determines the strength and shape of the future interaction. A compact body would deliver energy and momentum into a smaller area. A fragmented stream would distribute the same material more gradually. A dark matter-supported cloud could pass through the disk differently from a loose collection of gas. Current observations cannot tell us precisely which form will arrive. They do show that the Smith cloud has not crossed the halo without consequences. It is being worn down, rebuilt, slowed, and reorganized at the same time. Its impossible journey becomes possible only when we stop imagining one fixed cloud making the entire trip. What continues toward the Milky Way may be a dense remnant, a cooling wake, a magnetized interface, and perhaps an unseen gravitational structure travelling together for now. The main body of the Smith cloud is expected to reach the Milky Way's disk in roughly 27 to 30 million years. That prediction is based on its measured distance, direction, and three-dimensional velocity, combined with models of the galaxy's gravitational field. It is an estimate rather than a scheduled appointment. The cloud is losing material, the halo is slowing parts of it, and the Milky Way's gas is not distributed evenly. Each of those factors can alter where and when different portions arrive. The densest part may follow one route, while stripped fragments reach the disk earlier or spread into the halo before they get there. The phrase collision course therefore describes a broad future encounter, not one precise instant when the whole cloud crosses an invisible line. Some of the collision has already started. Gas removed from the Smith cloud is mixing with material belonging to the Milky Way. Radio observations show slower features around its main body, and its ionized envelope extends beyond the clearest neutral hydrogen. The galaxy is already taking material from the cloud, one disturbed filament at a time. The event in the distant future will begin when the surviving concentrations enter a much denser environment. The Milky Way's disk contains stars, dust, magnetic fields, cosmic rays, and gas at many temperatures. Some gas is hot and ionized. Some is warm and mostly atomic. Colder regions contain neutral hydrogen, while the densest clouds contain molecules that may eventually form stars. The disk is still extremely thin by earthly standards. A person somehow placed between its atoms would not experience anything resembling thick fog or seawater. Compared with the galactic halo, however, the disk is crowded. The increase in density changes everything for an incoming cloud. Ram pressure becomes stronger. Collisions between particles become more frequent. Shock waves form more easily, and the time available for the Smith cloud to adjust becomes shorter. Its leading edge will meet disk gas first. The two gaseous systems will not bounce apart like solid objects. They will push into each other, compress, heat, slow, and mix. A shock will travel into the Smith cloud, while another disturbance moves into the gas of the disk. Between them, pressure will rise and material will be forced into a turbulent region. The cloud's forward motion will begin converting into heat, random gas movement, compression, magnetic disturbance, and large-scale flow. This does not mean the impact region will become a glowing ball visible across the entire galaxy. Most of the energy will be deposited into interstellar gas far from the solar system and spread across an enormous area. The local consequences could still be significant. The Smith cloud contains several million solar masses of neutral and ionized material. Even if much of that mass disperses before arrival, the remaining gas will carry a great deal of momentum. When it meets the disk, it may push existing gas aside and produce a cavity. Material around the edge of that cavity could be compressed into a shell. Astronomers already observe large holes, arcs, and shells in the neutral hydrogen disks of galaxies. Many are created by supernovae and winds from massive stars. Others may result from the impacts of high-velocity clouds. Distinguishing between those causes is difficult because the final structures can look similar. A group of supernovae can inflate a bubble from inside the disk. An incoming cloud can create a cavity by pushing from outside. After millions of years, both may leave expanding shells, disturbed velocities, and regions where gas has collected around an empty-looking centre. The Smith cloud's future impact could produce one of these large structures in the outer Milky Way. Whether it drills a narrow passage, creates a broad depression, or dissolves near the surface depends on how concentrated it remains. A compact, dense cloud penetrates farther before being stopped. A diffuse cloud spreads its momentum across a larger area and is disrupted more quickly. The angle of arrival matters as well. The Smith cloud is not expected to strike vertically. It approaches the disk along an inclined route while continuing to orbit the galactic centre. This gives it a substantial sideways velocity relative to the gas it encounters. Instead of simply punching downward, it may plough through the outer layers at an angle, drawing out a long region of disturbed gas. Imagine pressing a spoon straight down into a bowl of thick soup. The disturbance is concentrated near the point of entry. Dragging the spoon diagonally through the surface creates a longer wake. The galactic disk is not soup, and the Smith cloud is not a spoon, but the direction of motion has the same practical importance. Its prograde orbit may soften part of the encounter, because it moves in the general direction of galactic rotation. The disk gas will not be travelling directly against it. The cloud still appears to have a different orbital speed, and it also has motion toward the plane. Those differences provide the relative velocity that drives the collision. As the leading gas slows, material behind it will continue arriving. This can compress the front further, rather like traffic collecting where a motorway narrows, except the vehicles are hydrogen atoms and the delay lasts considerably longer than the average commute. Compression has two possible effects that initially pull in opposite directions. It heats the gas, which can make it expand and resist collapse. It also raises the density, which can increase cooling and strengthen gravity. Immediately after a strong shock, gas may become too hot and turbulent to form stars. Star formation does not begin simply because two clouds meet. The heated gas must lose energy. Turbulent motion must decline or collect material into sufficiently dense regions. Molecules must form or survive, and gravity must overcome thermal pressure, magnetic support and internal movement. That process may require millions of years. A collision can therefore suppress star formation in one place and encourage it later in another. Near the most energetic part of the impact, shocks may ionize hydrogen and break apart existing molecules. Farther along the compressed shell, gas may cool and accumulate. If the shell becomes dense enough, it can fragment under its own gravity. Those fragments may develop into molecular clouds, and some of them may form stars. This delayed sequence is important because popular descriptions sometimes say that the Smith cloud will hit the Milky Way and create millions of stars. The cloud contains enough gas to contribute to the formation of a very large stellar population, but raw gas mass is not the same as a guaranteed number of stars. Only a fraction of gas inside a molecular cloud becomes stars before radiation, winds and supernovae disperse the remaining material. Some of the Smith cloud may stay warm, some may join the diffuse interstellar medium, some may be thrown back into the halo. The phrase, "enough material to form millions of suns," describes the scale of the supply. It does not mean that millions of stars will appear immediately after impact in one convenient group photograph. Researchers have used hydrodynamic simulations to test what the encounter might do to the Milky Way's star formation rate. These models cannot reproduce every detail of the real galaxy, so they usually examine a range of possibilities. One study tested clouds with masses of 1 million and 10 million times the mass of the Sun. The lower value represented a relatively modest surviving impactor. The upper value represented a deliberately large case, with much of the cloud's extended mass concentrated into the tip. In the lower mass simulation, the collision did not create a noticeable change in either the local or global star formation rate. The cloud disturbed the gas, but the disturbance was not enough to produce a clear burst of new stars. In the high mass case, the model produced a short increase in the Milky Way's total star formation rate. For about 5 million years, the increase reached roughly 1 solar mass of new stars per year, close to doubling the normal rate assumed in the simulation. That would be a major event for the region of impact, but the result depends on an extreme concentration of mass. The real Smith cloud may arrive in a more fragmented and less dramatic condition. The two simulations are useful because they show that the future is controlled by how much dense gas reaches the disk together. The arrival of 1 million solar masses spread across a large stream is different from the arrival of 10 million solar masses packed into one head. Current observations cannot tell us exactly what the cloud will look like after another 27 million years of stripping. Predictions of an enormous starburst should therefore be treated cautiously. A local increase is possible, a galaxy-wide transformation is not expected. The Milky Way contains tens of billions of stars and a vast reservoir of interstellar material. Even a cloud containing several million solar masses is small compared with the whole galaxy. Its impact will affect a region, not rearrange the entire disk. The event will also take place far from the solar system. The Smith cloud is heading toward the outer Milky Way at a galactocentric distance well beyond the Sun's orbit. Earth is not located at the projected crossing point. There is no risk of the cloud sweeping through the solar system, removing the atmosphere, pushing the Sun from its orbit, or requiring anyone to develop a hydrogen-resistant umbrella. Even if the impact produced a period of enhanced star formation, the region would remain thousands of light-years away. New massive stars formed that could eventually explode as supernovae, but distance greatly reduces their effect on Earth. A supernova needs to occur comparatively close to the solar system before becoming a serious biological threat. The Smith cloud is not expected to deliver such an event near us. There is also no single blast wave travelling from the impact site toward Earth with enough strength to damage the planet. Energy released into the interstellar medium spreads and weakens. The gas is thin, the distances are enormous, and the Milky Way contains many environments that interrupt and redirect expanding disturbances. From Earth, assuming intelligent observers are still here and using suitable instruments, the most interesting effects would be astronomical. Radio telescopes might see a new cavity or complex of high-velocity gas. Infrared telescopes could detect cold dust and developing molecular clouds. After enough time, ultraviolet and visible observations might reveal groups of young stars. The region could become a valuable example of star formation triggered or modified by an external gas flow. It would not resemble a sudden flash followed by a finished object. Astronomers would need to observe it across many generations to follow the full sequence. The first arrival of diffuse gas might begin hundreds of thousands or millions of years before the densest part. The strongest compression might last for several million years. Star formation could continue after the original cloud had lost its identity. Future astronomers might argue about where the Smith cloud ended and the new galactic gas structure began. That boundary is already unclear today. When cloud material mixes with the disk, individual atoms will no longer carry an observable label. Astronomers may distinguish the incoming gas for a while through its velocity and metallicity. As the motion slows and the composition blends with the surroundings, those clues will fade. The Smith cloud will stop being one named object and become part of the Milky Way's interstellar medium. This is the ordinary fate of incoming gas. A cloud can remain distinct only while its position, temperature, or velocity separates it from its surroundings. Once those differences disappear, the gas does not vanish. Its identity vanishes. Some hydrogen may cool into dense clouds, some may remain warm and atomic, some may be ionized by young stars. Some could eventually enter stellar interiors and take part in nuclear fusion. Other material may be expelled again by stellar feedback. The return of the Smith cloud could therefore begin another cycle, rather than complete one. The collision may also alter the chemistry of the impact region. The cloud appears to have a lower abundance of heavy elements than gas near the Sun, although it is not chemically pristine. Mixing it with outer disk gas could slightly dilute or redistribute elements in the region. If some of its mass condense from the halo, it may bring material with a different chemical history from the local disk. New stars forming from the mixture would preserve part of that composition in their atmospheres. Astronomers millions or billions of years later might use those abundances to reconstruct where the gas originated, though the evidence would be subtle. The disk itself will not remain fixed while the cloud approaches. Over the next 27 million years, stars and gas at the projected impact radius will continue orbiting the galactic center. Spiral features will move and change. Existing molecular clouds will form stars and disperse. The cloud's crossing point is therefore a prediction in a moving environment. It will meet whatever gas happens to occupy that region at the time, not the same structures astronomers map there today. A dense spiral arm segment would create a different encounter from a quieter gap between arms. If the cloud reaches an area containing substantial neutral gas, the collision may compress a large amount of material. If it meets a low-density region, it may pass farther through the disk before being stopped. Small differences in timing can change which environment lies in its path. This uncertainty is another reason simulations should be understood as examples rather than exact forecasts. Researchers build a model Milky Way with a chosen gas distribution, star formation prescription, and cloud mass. The computer then shows how that particular setup develops. The real Milky Way 27 million years from now will have details no present model can know. The large-scale physics remains predictable. Fast gas will generate shocks, momentum will be transferred, heating, compression, cooling and turbulence will follow. The exact pattern of holes, shells and stars is less certain. Magnetic fields could change the shape of the encounter. The disk contains fields generally aligned with its broad structure, though they bend and tangle around clouds and bubbles. The incoming Smith cloud also appears to be associated with magnetized ionized gas. When the two meet, their field lines may compress, reconnect or redirect flows. Magnetic pressure can make it harder for gas to collapse in some directions while guiding material along others. Reconnection can convert magnetic energy into heat and particle motion. A simulation that ignores magnetic fields may therefore produce a different fragmentation pattern from the real impact. Cosmic rays add another influence. These fast particles contribute pressure in the interstellar medium and interact with magnetic fields. Their role in a Smith cloud collision has not been mapped with confidence, but future models may include them as computing power and observations improve. Dark matter, if present, would create the largest difference. A gas-only cloud will be slowed and dispersed by the disk. An accompanying dark matter subhalo would feel gravity but almost no direct gas pressure. The invisible halo could pass through while the ordinary gas lagged behind. This separation might stretch the cloud, leave a gaseous wake in the disk, and allow the dark object to emerge on the other side. It might later collect some gas again. Simulations of dark matter-confined high-velocity clouds have produced a range of outcomes. Some retain a significant gas component after crossing. Others lose nearly all of it, leaving the dark halo to continue alone. If the Smith cloud has already crossed the disk once, a process like this may have helped create its current head and tail form. Its future encounter could repeat the separation more severely. No direct evidence confirms that such a subhalo exists, so the ordinary gas-only scenario remains equally important to study. Either way, most models expect the cloud to lose its current shape. The disk is simply too dense, and the collision too disruptive for an object this diffuse to pass through as though nothing happened. Its neutral core may split into many clumps. The ionized envelope may spread over a still larger region. The radio signal that now defines the Smith cloud could become a collection of smaller velocity features. For a time, astronomers might continue using the old name for the whole disturbed complex. Eventually, there would be no clear reason to do so. The loss of identity will be gradual enough that no one can select a single date and say the Smith cloud ceased to exist at noon. One survey may still detect a connected tail while another sees only fragments. A later study may classify the same material as part of an expanding shell in the outer disk. Scientific names follow recognizable structures, and structures change. The event may also create motion above and below the disk. Gas pushed downward can compress the lower layers and drive material through the plane. Gas displaced sideways can build ridges around the impact site. Some heated material may rise into the halo on the opposite side, producing another fountain-like flow. The Smith cloud may therefore arrive from the halo, only to send part of the affected disk gas back into the halo. This kind of circulation prevents a galaxy from separating neatly into incoming and outgoing material. One process feeds the next. A high-velocity cloud falls, its impact drives turbulence. Compression forms stars. Massive stars produce winds and supernovae. Those events launch new gas upward. The original Smith cloud could help create the conditions for a future generation of smaller clouds. The momentum it adds may also affect the outer disk's rotation and thickness. Because the cloud has substantial prograde motion, it transfers angular momentum as it merges. The effect on the entire Milky Way will be tiny, but the local gas can be accelerated or redirected. A sufficiently strong impact may contribute to warps, vertical oscillations or corrugations in the outer disk. The Milky Way's outer regions are already warped rather than perfectly flat. Interactions with satellite galaxies, dark matter and incoming gas all contribute to this structure. It would be difficult to isolate the Smith cloud's contribution after the fact unless the encounter produced a very distinctive feature. The cloud's motion may also generate turbulence that persists after the main gas has settled. Turbulence helps support the interstellar medium against gravity, mixes chemical elements, and shapes the density structure from which stars form. An impact can therefore influence star formation without immediately creating new stars. It changes the conditions under which future clouds develop. This brings us back to the word collision. In ordinary speech, a collision is brief. Two objects meet, energy is released, and the event ends. The Smith cloud's collision with the Milky Way is better understood as a long period of assimilation. It begins in the halo, where stripped gas joins the galaxy. It strengthens as the remaining cloud enters denser layers. It continues while shocks and turbulence spread through the outer disk. It remains relevant as compressed gas cools, fragments, and possibly forms stars. By the time that process settles, millions or tens of millions of years may have passed. There is no need for an observer to survive the entire sequence in order to study it. Astronomers examine similar processes at different stages throughout the universe. One galaxy shows gas approaching its disk. Another contains a fresh impact cavity. Another displays young stars around a compressed shell. By comparing many systems, researchers build a time sequence from separate examples. The Smith cloud is valuable because its distance and motion allow a future encounter to be predicted for an object within our own galaxy. It provides a rare chance to connect present conditions with a testable physical outcome, even though no living researcher will see the main crossing. The prediction can still improve science today. Models of the future impact must begin with the observed mass, velocity, temperature, and structure. If a model cannot carry those conditions forward realistically, it reveals missing physics in our understanding of gas clouds and galactic disks. Future observations of the cloud will refine those starting conditions. More sensitive radio maps may find additional neutral fragments. Ultraviolet spectra can measure chemical differences across the structure. Faraday rotation can improve the map of its magnetic field. Better models of the Milky Way's hot halo will change estimates of how quickly the cloud is stripped before arrival. The projected impact may become less dramatic if observations show that most of the cloud is diffuse and vulnerable. It may become more concentrated if dense material or an unseen confining mass is discovered. For now, the likely outcome lies between two extremes. The Smith cloud will not strike the galaxy as one solid intact body and produce an instant explosion. It will also not disappear without leaving any effect. Its gas is massive enough to matter locally, and its speed is high enough to disturb the outer disk. The strength of that disturbance depends on how much material remains concentrated. A cavity, compressed shell, turbulent wake, and period of enhanced local star formation are all physically reasonable possibilities. A catastrophic event for Earth is not. By the time the cloud's remaining gas settles, it will be difficult to separate from the material it encountered. Its hydrogen will have been heated, cooled, ionized, recombined, and mixed. Those regions will not remember the radio shape of the Smith cloud, or the name of the graduate student who first detected it. They will simply contain gas with enough density to begin the slow process of becoming something else. And that is where the story moves from an incoming cloud to the first conditions required for new stars. The hydrogen arriving from the halo is not ready to become stars immediately. Most of the Smith cloud is currently neutral atomic gas, meaning its hydrogen exists mainly as separate atoms rather than pairs of atoms joined into molecules. Stars usually form inside much colder and denser molecular clouds, where hydrogen is largely present as molecular hydrogen. Moving from one state to the other requires several changes. The incoming gas must slow down, cool, become compressed, and gain protection from the ultraviolet radiation that can break hydrogen molecules apart. It also needs dust grains, because the surfaces of those grains provide efficient meeting places where hydrogen atoms can join. Two hydrogen atoms passing each other in open space have difficulty forming a stable molecule. They need to lose energy during the encounter, or they simply separate again. A dust grain allows each atom to attach briefly to a surface, move around, encounter another atom, form a molecule, and leave with the extra energy transferred into the grain. Dust may represent only a small fraction of a cloud's mass, but it has a large influence on its chemistry and temperature. The Smith cloud appears to contain material enriched by earlier generations of stars, and observations suggest that at least some dust is present. This gives its gas a better chance of cooling and forming molecules than completely pristine hydrogen would have. The outer Milky Way also contains dust and heavier elements, though generally in lower proportions than regions closer to the galactic centre. When the cloud's gas mixes with the disk, the combined material will contain the ingredients needed for molecular chemistry. Before that chemistry can become efficient, the gas must become denser. The future collision provides one possible method. As the Smith cloud pushes into the disk, its leading material will be slowed. Gas arriving behind it will continue moving forward, creating compression. Disk gas will also collect around the impact region. Some will be pushed sideways, while some may become trapped between the incoming flow and denser galactic structures. Shocks can increase the density rapidly, but they also heat the gas. The first stage of the encounter may therefore produce hot, ionized material rather than a cold stellar nursery. Cooling begins after the compressed gas radiates away its excess energy. Atoms and ions emit photons when collisions raise their electrons into higher energy states, and those electrons later return to lower states. Carbon, oxygen, sulfur, and other elements provide important cooling channels. Dust grains can absorb energy and release it as infrared radiation. As the temperature falls, some protons capture electrons and become neutral hydrogen again. Denser regions cool more efficiently because their particles meet more often. The gas may pass through several phases rather than making one direct change from hot plasma to cold molecular material. It can begin ionized, become warm atomic gas, cool into a colder neutral phase, and eventually develop molecular regions inside its most shielded concentrations. Each phase occupies a different density and temperature range. They can coexist close together, especially in a turbulent collision zone. A warm layer may surround a cooler clump. Ionized gas may flow around neutral material. Thin molecular filaments can form inside a much larger atomic structure. Radio telescopes would trace the neutral hydrogen through its 21 centimeter emission. Infrared and millimeter telescopes would be needed to study dust and molecules. Ultraviolet observations would reveal hot young stars once they began to appear. The future transformation would therefore be seen differently, depending on the instrument used. Turbulence will decide where much of the dense gas collects. When the Smith cloud strikes the disk, the flow will not remain smooth. Shocks will meet, bend, and break into smaller structures. Gas travelling at different speeds will create shear. Magnetic fields will redirect some material while resisting compression in other directions. The result will contain eddies and irregular motions across many scales. Turbulence can prevent star formation by supporting gas against gravity. A rapidly moving parcel does not settle easily into a collapsing clump. Internal motion behaves like an additional form of pressure. The same turbulence can also produce star-forming pockets. Colliding streams create temporary zones of high density. Long filaments form where gas is squeezed between converging motions. At the intersections of those filaments, enough material can gather for gravity to become important. This is why compression does not lead to one uniform response. Most of the affected gas may remain too warm, too diffuse, or too turbulent to collapse. A smaller fraction may enter unusually dense regions where cooling becomes rapid and gravity begins to win. Molecular clouds are not smooth balls. Observations show tangled networks of filaments, clumps, and cores. Their internal gas moves at speeds greater than would be expected from temperature alone. Stars form mainly in the densest parts of this structure, not evenly throughout the cloud. A large amount of hydrogen can therefore remain inside a molecular cloud without ever entering a star. The existence of molecular gas is an important step, but it does not guarantee collapse. Gravity must overcome several competing effects. Thermal pressure comes from the random motion of particles. Turbulent pressure comes from larger irregular flows. Magnetic fields resist some forms of compression. Rotation can prevent material from falling directly inward. External radiation may heat the gas, while collisions or nearby stellar activity can tear a clump apart. For a region to collapse, it needs enough mass within a small enough volume. If a clump is too light or too warm, pressure disperses it. If it becomes sufficiently massive and dense, its self-gravity strengthens until the gas begins falling inward faster than internal support can stop it. Astronomers sometimes describe this threshold using the Jeans mass. The exact value depends mainly on temperature and density. Cold, dense gas can collapse in smaller amounts than warm, thin gas. Cooling is therefore not merely a change in comfort. It determines how easily gravity can organise the material. The Smith cloud's impact could create many concentrations that briefly exceed this threshold. Some will continue collapsing, others will be disrupted before they get far. A collapsing region does not fall inward as one perfectly even sphere. Small density differences grow. The larger clump breaks into smaller cores, each of which may become a star or a compact multiple star system. This fragmentation is one reason stars often form in groups. A single compressed complex created by the impact could produce hundreds or thousands of dense cores. The number would depend on the amount of cool gas, the degree of turbulence, the magnetic field, and how quickly feedback begins. The first objects inside those cores would be protostars. A protostar forms as gas falls toward a growing central concentration. Gravitational energy is converted into heat, making the center warmer and brighter even before normal hydrogen fusion begins. Because the collapsing material has some rotation, it cannot all fall directly into the center. As the cloud contracts, its rotation becomes faster, much as a skater spins more rapidly after pulling in their arms. Gas settles into a flattened disk around the protostar. Material from that disk continues feeding the central object. Magnetic fields and rotation help launch narrow jets from the young system. These jets travel away along the rotational axis and collide with the surrounding cloud. A newborn star is therefore not a quiet object hidden inside undisturbed gas. It begins influencing its surroundings while it is still growing. The protostar continues contracting until its core becomes hot and compressed enough for hydrogen fusion. At temperatures of around 10 million degrees, hydrogen nuclei begin combining into helium, releasing energy. The object has then entered the long, stable part of its stellar life. NASA describes this broader sequence as beginning in cold molecular clouds, where dense pockets collapse, form protostars and disks, and eventually become fusion-powered stars. These stars would not all have the same mass. Most would probably be smaller and cooler than the Sun. A smaller number would resemble the Sun, and only a tiny fraction would become very massive stars. That small fraction would have an influence far greater than its numbers suggest. Massive stars release intense ultraviolet radiation that ionizes nearby hydrogen. Their winds blow cavities in the surrounding cloud. After only a few million years, the most massive explode as supernovae. These processes begin removing and heating the remaining gas. Star formation therefore contains its own stopping mechanism. The first stars to appear can interrupt the formation of later ones. Their radiation and winds may disperse a cloud before most of its material has time to collapse. Some expanding bubbles compress nearby gas and produce additional stars along their edges. Other bubbles destroy dense structures or separate protostars from the reservoirs that were feeding them. Feedback can both trigger and suppress star formation, sometimes within the same region. A shock from one massive star may compress a neighbouring clump. The ultraviolet radiation following it may then erode the clump before it converts much gas into stars. The balance depends on timing, geometry, density, and distance. This is why the total mass of the Smith cloud should never be converted directly into a final number of newborn stars. NASA has described the cloud as containing enough material to make about 2 million suns. That comparison communicates the scale of its gas supply. It does not mean the Milky Way will receive exactly 2 million sun-like stars. A considerable portion of the gas will remain outside stars. Some will be heated and dispersed. Some will become part of low-density disk material. Some may be sent back into the halo. Even within ordinary molecular clouds, only a limited part of the available mass reaches stars before feedback and turbulence alter the cloud. Reviews of molecular cloud star formation find that only a small fraction of cloud material is channeled into collapsing protostars during a typical gravitational freefall time. The Smith cloud could therefore contribute enough material for millions of solar masses of stars in principle, while producing far fewer stars in practice. The eventual count would also depend on the masses of those stars. 1 million solar masses of star formation could create more than 1 million individual stars because most stars have less mass than the Sun. A smaller total stellar mass might still produce a very large population of dim red dwarfs. Astronomers are more likely to describe the result through the total mass of stars formed, or the star formation rate, than through one exact star count. The rate would tell them how many solar masses of gas become stars during a given period. The Milky Way currently forms roughly one or a few solar masses of stars each year, depending on the method and boundaries used. The Smith cloud's future impact might add a local increase, but simulations show that the size of that increase is highly sensitive to the mass that remains concentrated at arrival. A hydrodynamic study tested two deliberately different cases. The lower mass model used a cloud containing 1 million solar masses. Its impact produced no noticeable change in either the total galactic star formation rate or the rate near the collision site. The gas was disturbed, but that disturbance did not lead to a measurable burst of stellar birth. The high-mass model placed 10 million solar masses into the cloud's tip, an intentionally extreme assumption compared with observations. That impact produced a short increase lasting roughly 5 million years, with the additional galactic star formation rate reaching about 1 solar mass per year. Under the model's assumptions, this nearly doubled the Milky Way's normal rate for a limited period. The researchers emphasized that the upper case was conservative in a different sense from ordinary speech. It concentrated the entire extended cloud mass into the impactor's leading region, creating the strongest reasonable test. The real Smith cloud is spread across a long head and tail structure, and will probably become more fragmented before it reaches the disk. Its true effect may therefore resemble the lower case, the upper case, or something between them. The simulations demonstrate what is possible under specified conditions rather than supplying a guaranteed forecast. The collision may also form stars without producing a clear change in the Milky Way's overall rate. A local cluster can be significant to astronomers while remaining too small to alter a measurement averaged across the entire galaxy. Suppose the impact triggers a large stellar association in one outer disk region. The association might contain thousands of stars and reshape its surroundings, yet the rest of the Milky Way would continue forming stars elsewhere. Against the background of the whole galaxy, the increase could be difficult to identify. This distinction between local and global effects matters. The Smith cloud will not need to create a galaxy-wide starburst to influence the outer disk. A few new molecular complexes, shells, and stellar groups would still represent a meaningful transfer of material from the halo into the next generation of stars. There is also a possibility that the cloud has already formed a very small number of stars. Researchers have searched its current position for young, hot O-type and B-type stars that might have formed within the gas. Such stars would be useful because they are luminous and short-lived. If they shared the cloud's distance and distribution, they could indicate recent star formation. One study used ultraviolet and infrared survey data to select candidate young stars projected against the Smith cloud. The researchers found a slight excess compared with a control region, but the result was not statistically significant. Foreground stars' dust extinction and the cloud's low position near the crowded galactic plane made the search difficult. The study could not confirm a young stellar population, but it also could not completely rule out star formation at a very low rate. A small population similar to that of a faint gas-rich dwarf galaxy might have escaped detection. For now, the Smith cloud is treated as effectively starless. Its average density is too low for widespread molecular gas and efficient star formation. The cloud contains dense areas compared with the halo, but not the deeply shielded cores common in active stellar nurseries. This explains why its millions of solar masses remain dark. Mass must be concentrated, not merely present. A warehouse containing enough timber to build 1,000 houses is not a town. The material needs to be moved, shaped, joined, and organized. The Smith cloud contains the raw hydrogen, but the collision with the disk may provide the compression and cooling needed to organize part of it. The outer disk could assist by supplying existing structures. The cloud may encounter atomic gas arranged into filaments or shells. It could strike the edge of a molecular complex rather than a uniform layer. If the incoming flow meets an already dense cloud, the combined pressure may push some regions toward collapse more effectively than an impact into diffuse gas. On the other hand, too much relative speed can shred the molecular cloud, increase turbulence, and delay star formation. Cloud collisions do not always trigger stars. Their outcome depends on whether compression creates stable, dense layers faster than shocks and turbulence disperse them. Reviews of cloud-cloud collisions show that such encounters can collect mass into compact regions and may promote massive cluster formation under suitable conditions, but they are not universal switches that turn star formation on whenever two gas structures meet. The Smith cloud's unusual scale makes its encounter more complicated than a collision between two ordinary molecular clouds. Most of its material will begin as atomic or ionized gas rather than as one cold molecular body. It may enter the disk across a region thousands of light years long. Different parts will meet different environments and arrive at different speeds. One fragment may create a shock that cools efficiently. Another may dissolve into warm gas. A dense core may penetrate farther before stopping, while a diffuse section spreads along the surface of the disk. There may be no single type of star-forming outcome. Some areas could produce young stars within a few million years of the strongest compression. Other areas might need much longer to gather into molecular clouds. A portion of the gas may orbit the galaxy for tens of millions of years before eventually entering a star-forming region unrelated to the original impact site. When astronomers say the Smith cloud will trigger star formation, the word trigger may therefore include several routes. The most direct route is shock compression at the impact site. A second route is the creation of a large shell whose edges later become gravitationally unstable. A third route is the gradual addition of gas to the outer disk, increasing the reservoir available for unrelated molecular clouds to form later. The cloud can contribute to stellar birth even if no star forms immediately where its leading edge first arrives. Its heavy elements and dust would join the same cycle. Those materials are important because a star-forming cloud is not made only of hydrogen. Helium contributes substantial mass. Carbon, oxygen, silicon, iron, and other elements affect cooling and chemistry. Dust grains shield molecular gas from radiation, and later become part of the disks around young stars. Inside those disks, solid particles collide and grow. Some may eventually form asteroids, planets, moons, and smaller debris. This does not mean the Smith cloud is carrying completed planets into the Milky Way. It means that material once processed by older stars may later become part of new planetary systems. An oxygen atom in the Smith cloud might have been produced inside a massive star long before the cloud's current journey. After the impact, it could enter a molecular cloud, freeze onto a dust grain, become part of a protoplanetary disk, and eventually join a planet or remain inside a new star. The sequence would involve many uncertain steps, but none requires special physics. It is the normal recycling of matter inside a galaxy. Stars do not create most hydrogen, but they transform some of it into heavier elements. When they die or lose material, those elements return to space. Galactic flows then carry the enriched gas into new environments. The Smith cloud is valuable because it may show this cycle on a large and measurable route. Disk gas pushed into the halo, mixed with the corona, and returned to another part of the disk. Future stars formed from its material would not be the end of that route. Low-mass stars would preserve much of their material for billions or trillions of years. Massive stars would use their fuel rapidly and return gas to space after only a few million years. Their winds and explosions could build new bubbles and launch another outflow. The same region that received the Smith cloud might eventually send some of its gas back toward the halo. That creates an interesting possibility. A galactic fountain may return material, help form massive stars, and then receive material from those stars when they die. The cycle does not close neatly because gas mixes at every stage. Some remains in the disk, some escapes to the halo, some is locked in long-lived stars and planets. The Milky Way continually changes the distribution, temperature, and chemical form of its matter. A future observer might see young clusters near the Smith cloud's impact site and measure their chemical abundances. The stars could contain slightly different ratios of elements from neighbouring populations, reflecting the mixture of incoming cloud gas and outer disk material. Their motion might also preserve a trace of the collision. If the incoming gas carries a different velocity, newborn stars could begin with small departures from the normal motion of the disk. Over time, galactic rotation and gravitational interactions would spread the stellar population. An open cluster may remain recognizable for millions or hundreds of millions of years before its members drift apart. A loose stellar association can disperse much sooner. The new stars would gradually stop looking like one group linked to a former high-velocity cloud. Astronomers trying to reconstruct the event long afterward would search for chemical similarities, unusual velocities, and nearby gas structures. The task would be similar to the one faced today when studying possible ancient cloud impacts. Cavities and stellar groups survive, but their original cause is difficult to identify. There is evidence that other high-velocity clouds have struck the Milky Way. Astronomers have reported a compact high-velocity cloud aligned with a kiloparsec-scale hydrogen supershell in the outer galaxy, interpreting the pair as a possible impact that occurred about 5 million years ago. Such systems provide examples of how incoming gas can inject energy and momentum into the disk, though each case has its own uncertainties. The Smith cloud offers the opposite view. Rather than examining a suspected impact after it happened, we see the incoming structure before the main disk crossing. That gives researchers time, in the astronomical sense, to study its initial conditions. Its neutral and ionized mass can be estimated. Its magnetic environment can be mapped. Its chemical abundance can be measured, and its speed can be reconstructed. These data allow simulations to begin with a real object rather than an invented generic cloud. No model will follow the future perfectly, but each can test which physical conditions produce molecular gas, dense cores, and star formation. The results may also clarify what is required for a high-velocity cloud to matter. Perhaps most incoming clouds dissolve into the halo and feed the disk indirectly. Perhaps only the densest ones create recognizable impact regions. Perhaps the most important contribution is not triggered star formation, but the steady delivery of gas over long periods. The Smith cloud is large enough to test all three possibilities. By the time any newborn stars appear, the original cloud may no longer be recognizable. Its gas will be divided among shocks, shells, filaments, molecular complexes, and the diffuse disk. The name Smith cloud may survive in historical records even after the physical boundary has disappeared. Its material will continue under new descriptions: atomic hydrogen, molecular gas, protostellar core, accretion disk, main sequence star, stellar wind, supernova remnant. None of those changes destroys the matter. They change its arrangement and the energy it carries. The path from wandering gas to newborn stars is therefore not one event. It is a sequence of compression, cooling, chemical change, gravitational collapse, and feedback. Only a fraction of the cloud will complete the full sequence, and no measurement today can tell us exactly how large that fraction will be. The important point is that the Smith cloud represents usable galactic fuel. It is not useful because every atom is certain to become part of a star. It is useful because star-forming galaxies require a continuing supply of gas, and the cloud is one visible example of that supply moving toward the disk. Following its route forces astronomers to ask how the Milky Way receives gas, how long that gas remains in the halo, how it mixes with older material, and how efficiently it becomes part of the next stellar generation. Those questions extend far beyond one high-velocity cloud. They concern the way the entire Milky Way maintains itself, regulates its star formation, and exchanges material with the space surrounding it. The Smith cloud is useful because it challenges the simplest picture of a galaxy. In that simple picture, the Milky Way is a flat collection of stars rotating around a bright centre. Gas sits between the stars, spiral arms move around the disk, and everything important happens inside the familiar band that we can see across a dark sky. The real Milky Way extends much farther. Its thin stellar disk is surrounded by a large region containing dark matter, old stars, globular clusters, magnetic fields, energetic particles, and gas at many different temperatures. Astronomers call the gaseous region around a galaxy the circumgalactic medium, often shortened to CGM. The boundary of this medium is not marked by a sharp surface. Gas becomes thinner with distance, and the outer halo gradually meets the material between galaxies. This extended atmosphere is difficult to detect because much of it is extremely diffuse. It may be hot enough to produce X-rays, cool enough to absorb ultraviolet light, or concentrated enough to emit radio waves from neutral hydrogen. No single telescope sees all of it. Astronomers combine radio observations, ultraviolet absorption, X-ray measurements, optical emission, and computer simulations. Each method traces a different temperature or ionization state. The Smith cloud passes through several of these conditions at once. Its core contains neutral hydrogen. A wider envelope contains ionized gas. Warm material lies in its disturbed boundary, while the surrounding corona is far hotter. This makes the cloud a moving probe of the Milky Way's halo. Researchers cannot place a thermometer, pressure gauge, or magnetic compass several thousand light-years below the disk. They can, however, observe how the Smith cloud responds to its environment. The amount of material removed from the cloud constrains the density of the surrounding gas. Its slowing fragments reveal drag. The ionized envelope provides information about radiation and collisions. The bent magnetic field around its leading region reveals how magnetized plasma flows around a large obstacle. In this way, the cloud makes the invisible halo easier to study. The halo itself is faint, but its effects on the cloud are measurable. A similar principle is used in everyday situations. Wind is difficult to see directly, but moving branches reveal its strength and direction. Water currents become visible when they carry sediment. The Smith cloud's tail is the equivalent of those moving branches. Its disturbed hydrogen tells us that the Milky Way's apparently empty surroundings contain enough matter to reshape an object thousands of light-years long. The cloud also reveals that the halo is not simply a storage area. Gas moves through it in both directions. Some material falls toward the disk. Some is driven outward by stellar winds and supernovae. Some may arrive from satellite galaxies or from the wider intergalactic environment. Outflowing and infalling gas meet, mix, cool, and change direction. The circumgalactic medium is therefore both a reservoir and a processing region. It receives material from the disk, holds and mixes it, and supplies gas that can later return to regions where stars form. Modern reviews of the circumgalactic medium describe it as a source of star-forming fuel, a location where galactic feedback operates, and an important regulator of a galaxy's gas supply. The Smith cloud gives that broad idea a specific form. It contains several million solar masses of neutral and warm ionized gas. It is losing material to the Milky Way, and the gas it transfers carries angular momentum as well as mass. It therefore changes not only how much material the galaxy contains, but also how some of that material moves. Angular momentum is the property that keeps material orbiting rather than falling directly toward the galactic centre. A parcel of gas moving around the Milky Way carries angular momentum according to its mass, distance from the centre, and rotational speed. When the Smith cloud mixes with other gas, momentum is exchanged. The cloud slows relative to its original motion, while the surrounding material may be pushed in the prograde direction. The effect on the entire Milky Way is small. The galaxy is vastly more massive than the cloud. Locally, however, the added motion can influence how gas settles into the disk. This is important because a galaxy cannot be fueled by mass alone. Incoming gas that has very little rotational motion falls inward differently from gas that already travels in the same direction as the disk. Gas arriving against galactic rotation can create strong shocks and lose energy quickly. The Smith cloud's prograde motion allows it to join the Milky Way in a more complicated way. It adds material while also contributing to the rotational flow. The cloud may therefore help astronomers understand how accreting gas becomes part of a rotating galaxy. Accretion is often described as though a galaxy simply collects material through gravity. In reality, incoming gas must adjust its temperature, velocity, chemical composition, and angular momentum. A cloud cannot become part of the disk merely by crossing into it. It must slow relative to nearby gas, mix, cool, and settle into a compatible orbit. The Smith cloud shows that this process begins long before the main body reaches the plane. Its stripped tail is already being absorbed into the galactic environment. Smaller fragments are already moving closer to ordinary Milky Way velocities. The transition between cloud and galaxy occurs gradually. A discovery published in 2023 made this picture even more interesting. Greenbank telescope observations identified what researchers called a leading component associated with the Smith cloud. This component contains dozens of smaller neutral hydrogen clouds with motions consistent with the larger Smith system. Many show evidence of interacting with gas in the disk. The leading structure appears to be crossing the galactic plane now, even though the main Smith cloud remains below the disk and is expected to arrive millions of years later. Its neutral hydrogen mass may approach 1 million solar masses, and the complete structure could stretch around 7 kiloparsecs across the sky. This result changes the simple image of one isolated object heading toward one future collision. The Smith cloud may be the most obvious section of a much longer gas stream. A leading portion has already travelled ahead, become fragmented, and begun entering the Milky Way. The familiar comet-shaped cloud would then be one large concentration within a broader structure rather than the entire incoming system. There appears to be a gap between the leading component and the main cloud. That gap could represent material that has become too diffuse, ionized, or mixed to detect clearly in neutral hydrogen surveys. It could also reflect genuine separation produced by different motions and interaction histories. Either way, the leading component provides a present-day example of the process previously discussed as a future event. Astronomers do not need to wait 27 million years to study every aspect of the encounter. Part of the wider system may already be showing what happens when fast gas reaches the disk. The smaller leading clouds are interacting with galactic material, slowing down and adding both mass and angular momentum to the interstellar medium. They can be examined for signs of compression, fragmentation, heating, and possible connections with local star-forming regions. The main Smith cloud may not repeat that behavior exactly because it is larger and may contain denser gas. The leading component still offers a valuable comparison. It shows that accretion can take place through a sequence of separated clouds rather than one intact body. That finding also demonstrates why better observations can change the apparent size of an astronomical object. The Smith cloud did not suddenly grow in 2023. Researchers found additional material whose velocity and behavior linked it to the known system. The same may happen again. More sensitive radio surveys could detect fainter, neutral gas between the two components or farther along the orbit. Ultraviolet observations may reveal ionized material where neutral hydrogen is absent. The object currently called the Smith cloud could eventually be understood as one part of an even larger circulation pattern. This would not make the earlier measurements wrong, it would place them inside a wider structure. The cloud's chemistry reveals another part of the Milky Way's behavior. If galaxies only consumed gas and never recycled it, their chemical structure would develop differently. Heavy elements created by stars would remain concentrated near their birthplaces, and gas pushed out of the disk would be permanently lost. the Smith cloud contains a substantial abundance of sulfur and other processed elements. Hubble measurements found an average sulfur abundance close to half the solar value, consistent with enriched material associated with the Milky Way's outer disk. This indicates that the gas has been influenced by stars before. It may have originated in the disk, collected enriched halo gas, or mixed with material expelled by previous stellar generations. Whatever the exact route, the cloud is not simply a parcel of untouched hydrogen, arriving for the first time. The Milky Way appears to be receiving some of its own processed material again. This recycling helps spread elements through the galaxy. A group of massive stars may release oxygen, sulfur, silicon and other elements into nearby gas. An energetic outflow can then carry that gas away from the disk. During a halo journey, it mixes with material from other regions. When it returns, it may enter a different part of the Milky Way. New stars forming there inherit a chemical mixture shaped by several earlier stellar populations. The cloud therefore shows how galaxies redistribute the products of nuclear fusion. The atoms created in one region do not remain there permanently. Winds, explosions, fountains, and accretion flows move them across thousands of light years. Recent conference results have added another chemical clue. Hubble observations presented in 2024 and 2025 reported gas phase depletion patterns consistent with dust in the Smith cloud. The researchers argued that the presence of dust, together with the enriched metallicity, makes a Milky Way origin more likely. These findings were reported in conference abstracts and still require the full scrutiny given to a complete peer-reviewed analysis, but they provide an important direction for further work. Dust is relevant because it is closely connected to processed galactic material. Dust grains contain elements made in stars and released into space. They affect cooling, molecular chemistry, and the shielding of gas from radiation. A dusty Smith cloud would support the idea that at least part of the object has passed through environments where stars formed and died. It would also affect the cloud's future. Dust could help its denser gas cool and form molecules after entering the disk, although shocks may destroy some grains during the collision. The unusual chemical measurements also reveal the difficulty of studying a mixed object. Sulfur, nitrogen, oxygen, silicon do not always give identical abundance estimates. Different lines of sight pass through different parts of the cloud. The main body may have one composition, while the tail contains more halo gas. Dust removes some elements from the gas phase, making them appear less abundant unless the depletion is considered. Ionization corrections add further uncertainty because observations may detect one ion of an element while other ions remain unseen. The disagreement between measurements is not merely an inconvenience. It tells astronomers that the Smith cloud is chemically structured and actively changing. A cloud that had remained isolated and well mixed would be easier to interpret. The Smith cloud has passed through a complicated environment, so its composition records several processes at once. Its chemistry can reveal its history only when combined with its motion, morphology, and interaction with the halo. The cloud also tests ideas about dark matter. The Milky Way is expected to contain many dark matter subhalos, some of which may contain few or no stars. If the Smith cloud were confined by one, it could represent a rare way to detect such an invisible structure through the gas held by its gravity. The proposed dark halo could help explain the cloud's survival and a possible earlier passage through the galactic disk. No direct evidence has confirmed this idea. The enriched chemical composition makes a simple, starless dwarf galaxy origin less likely. A dark subhalo would need to capture or retain processed Milky Way gas. The absence of a confirmed stellar population also means astronomers cannot trace an orbit through the motions of stars. The Smith cloud therefore places limits on what a dark matter explanation must accomplish, even if it does not prove that such a halo exists. A successful model must preserve enough gas, reproduce the observed head and tail structure, match the chemical composition, and account for the cloud's prograde velocity. This is scientifically valuable. objects that are difficult to explain force models to include more of the real physics. The magnetic field around the Smith cloud provides another measurement of the galaxy's surroundings. Faraday rotation observations of more than 1,000 background radio sources indicate that magnetic field lines are draped over the ionized gas and compressed near the head. The inferred line-of-sight field reaches at least several microgauss in parts of the system. This tells astronomers that magnetic fields in and around the galactic halo are not passive decorations. They can influence how gas mixes, how heat travels, and how instabilities develop. They may help dense fragments survive longer or shape the filaments in the cloud's wake. The Smith cloud becomes a tool for testing magnetohydrodynamics on a scale that cannot be reproduced in a laboratory. Researchers can compare the observed field shape with simulations and determine which flow conditions produce the same pattern. If a model creates the correct cloud shape but the wrong magnetic configuration, it is incomplete. If it reproduces the field but destroys the neutral gas too quickly, another process is missing. The cloud also reveals how limited the view from inside the Milky Way can be. Astronomers studying distant galaxies can sometimes see an entire disk and its surrounding gas from the outside. They observe streams, fountains, warps, and interacting companions in one broad image. We cannot obtain that external view of our own galaxy. The Sun sits inside the disk, so features overlap along every line of sight. Distances are difficult to measure, and foreground gas can hide structures farther away. The Smith cloud became unusually valuable because researchers could constrain both its distance and its full three-dimensional motion. Most high-velocity clouds do not have such well-known trajectories. Its leading section was measured at a total space velocity near 300 km per second, with motion toward the galactic plane, and its main body was shown to be shedding material into the Milky Way. This combination of information allows astronomers to do more than describe an unusual radio feature. They can estimate where it has been, how it interacts with the halo, and where its gas is likely to go. The uncertainties remain substantial, but the Smith cloud is closer to a controlled case study than most objects in the circumgalactic medium. It also reminds us that classifications can hide continuity. Astronomers use separate names for the interstellar medium in the disk, the circumgalactic medium in the halo, and the intergalactic medium between galaxies. Those categories are useful, but gas moves between them. A parcel may begin in the interstellar medium, be pushed into the circumgalactic medium, mix with external gas, and fall into the disk again. Another parcel may leave a satellite galaxy, enter the Milky Way's halo, and eventually join the interstellar medium. The physical material does not change category because it crosses a perfectly defined border. The names describe where it is and how it behaves at a particular time. The Smith cloud sits directly across those categories. Its possible origin lies in the disk. Its current body occupies the halo. Its leading component may already be entering the disk again. It is one connected example of the exchange between regions that are often studied separately. This exchange helps explain how the Milky Way can continue forming stars after billions of years. The galaxy still contains gas, but stellar formation and feedback continually alter that supply. Some gas becomes locked inside long-lived stars, some returns through winds and supernovae, some is heated until it cannot collapse easily, some escapes from the disk, while additional material arrives through the halo. Maintaining star formation requires a balance among these flows. The Smith cloud is not large enough to sustain the entire Milky Way by itself. Its several million solar masses represent a limited contribution when compared with the galaxy's total gas reservoir and long-term needs. Its importance comes from being one visible example. If many smaller clouds and a few streams perform similar deliveries, their combined effect can matter greatly. The Smith cloud demonstrates that the mechanism is physically active. It also shows that the difference between fresh fuel and recycled fuel may be difficult to define. The cloud contains galactic metals, but some of its mass may have condensed from the corona. Its atoms may have several origins. A fountain can carry enriched material outward and cause lower density halo gas to cool into its wake. The returning structure then contains more mass than the original outflow. The Milky Way gains gas from the halo through a process initiated by gas that left the Milky Way. This is not a contradiction, it is a feedback loop. The cloud reveals that galactic growth does not always involve large objects arriving from far beyond the halo. It can occur through local circulation that encourages surrounding material to cool and join the disk. The exact balance between truly external accretion and recycled galactic gas remains one of the larger unanswered questions. The Smith cloud cannot solve it alone, but it gives researchers a nearby case in which chemistry, velocity, gas phases, and magnetic structure can all be measured. Better instruments will improve that case. Future radio surveys will map neutral hydrogen with greater sensitivity and resolution. They may trace the connection between the main cloud and its leading component. Ultraviolet telescopes can examine more background sources, producing a chemical map rather than a few individual lines of sight. X-ray observations may constrain the hot corona surrounding the cloud. Larger samples of Faraday rotation measurements can improve the magnetic model. Numerical simulations will include finer structure, cooling, magnetic fields, cosmic rays, and a more realistic galactic disk. The main questions are clear. How much of the cloud began in the Milky Way? How much material has it collected from the corona? Is dark matter involved? How long can its dense gas survive? How much mass is already entering the disk through the leading component? Will the main body trigger significant star formation, or will it dissolve into the outer Milky Way gradually? Each answer will reveal something about the galaxy rather than merely about the cloud. This is why the Smith cloud remains important after more than 60 years of study. It began as an unusual radio signal. It became a map of high-velocity hydrogen. It then became a test of the galactic halo, chemical recycling, magnetic fields, gas accretion, and star formation. The more carefully astronomers study it, the less isolated it appears. It belongs to a larger stream, a larger halo, and a larger cycle moving matter between the disk and the space around it. The Milky Way is not a sealed system filled once with a permanent supply of gas. It is an active environment that receives, loses, and reuses material. The Smith cloud gives us one of the clearest nearby views of that activity. It shows gas being removed at the edges, gas joining the disk ahead of the main body, and enriched material returning toward regions where it may be used again. The object appears enormous when compared with the solar system, but it is one part of a galaxy-wide circulation that has operated for billions of years. Once we understand that wider process, the cloud's future arrival looks less like an isolated disaster and more like a large example of something galaxies must do to remain active. Gas leaves, gas cools, gas returns. Some become stars, while some begins the journey again. The Milky Way has been carrying out this exchange since long before the Sun formed, and it will continue after the Smith cloud's present shape has disappeared. That brings us back to the quiet object with which we began. A vast concentration of hydrogen moving through a region our eyes cannot see, gradually transferring its material to a galaxy that is still changing. At the start, the Smith cloud appeared to be one giant object racing toward the Milky Way. We now know that this simple description leaves out most of the story. The cloud is already inside the Milky Way's extended halo. It is not approaching the galaxy from a completely separate location. It travels through a hot, thin atmosphere surrounding the stellar disk. Most of its motion carries it around the galactic center, while a smaller component brings it toward the plane. It is moving quickly, but the distance remains so great that the main body will need tens of millions of years to reach the disk. The cloud is also not one solid object. It contains denser neutral hydrogen, a wider ionized envelope, disturbed fragments, and a long tail shaped by interaction with the halo. Its gas is being stripped, slowed, heated, cooled, and mixed. Some material may already have become part of the Milky Way. A leading component associated with the same system appears to be crossing the galactic plane now, showing that the delivery is spread across a much larger structure and a much longer period than the familiar image suggests. The words giant gas cloud can make the Smith cloud sound like something with a clearly defined surface. It has no such surface. Its density fades into the surrounding medium. Different instruments detect different boundaries. A radio telescope maps neutral hydrogen. An ultraviolet spectrograph detects atoms and ions by the light they absorb. Optical instruments trace faint hydrogen emission. Faraday rotation reveals magnetized plasma. Computer models connect those observations into a three-dimensional physical picture. There is no one image that contains the entire cloud. That is one reason it remained hidden for so long. If human eyes could detect 21 centimeter radio emission, the object would cover a large part of the sky. It would appear far wider than the moon. Our eyes cannot detect that wavelength, so the same region looks ordinary. Stars shine through it, and the dark spaces between them provide no obvious sign that millions of solar masses of gas lie in that direction. The Smith cloud is not hidden because it is small. It is hidden because human vision samples only one narrow part of the electromagnetic spectrum. Gail Smith noticed the cloud because its hydrogen moved at an unexpected velocity. The discovery did not begin with a detailed photograph or a prediction that one particular object should exist. It began with data that did not match the ordinary rotation of galactic gas. That unusual signal led to more observations. Those observations showed a comet-like structure. Better velocity measurements revealed its motion. Distance estimates gave it a physical size. Hubble spectroscopy measured sulfur and linked the cloud chemically with processed galactic material. Magnetic observations showed field lines compressed around its ionized gas. A single inconsistency in a radio survey eventually became a broad study of how the Milky Way exchanges matter with its halo. The cloud's name remains plain after all of this. Smith Cloud sounds closer to a local weather forecast than to an object 11,000 light-years long. That contrast may be useful. Astronomical objects do not become more physical when their names sound dramatic. A modest name can belong to an immense structure, just as a complicated name can belong to something too small to see without a microscope. The measurements matter more than the label. The current measurements tell us that the Smith cloud contains at least 1 million solar masses of neutral hydrogen, with additional mass in ionized gas. Its main structure extends for thousands of light years. It moves through the halo at close to 300 kilometers per second and shows clear signs that the Milky Way is pulling material away from it. Its chemistry tells us that at least much of the material has been enriched by stars. The cloud may have been launched from the outer disk, mixed with the surrounding corona, and returned along a long galactic orbit. A different model could involve a dark matter subhalo that collected Milky Way gas. The exact origin is still debated. The uncertainty is not a failure. Science often narrows possibilities without selecting one complete answer immediately. The sulfur abundance makes a simple, pristine intergalactic origin less likely. The trajectory supports a close connection with the Milky Way. The large mass and survival problem leave questions about how the cloud was launched and what keeps it together. New evidence can strengthen one interpretation or reveal that several processes contributed. The Smith cloud may never receive one simple origin sentence because it may not have one simple origin. Its present material can include gas expelled from the disk, gas collected from the corona, and material mixed in during earlier interactions. The atoms do not need to share one birthplace for the cloud to move as one recognizable system. We often name a river even though its water comes from rain, springs, melting snow, and smaller streams. The Smith cloud can be understood in the same practical way. It is a connected flow whose contents have changed. Its survival also becomes less impossible once we stop requiring every original atom to complete the journey. Dense clumps last longer than diffuse gas. Cooling can rebuild cold material in the turbulent wake. Magnetic fields can reduce some forms of mixing. Prograde motion lowers the relative headwind. An unseen dark matter halo could provide additional gravity, though it has not been confirmed. The object may also be the remaining portion of something that began much larger. Together, these mechanisms allow a large high-velocity structure to persist while losing and replacing material. What survives is the moving concentration, not a sealed parcel. The future encounter with the disk will continue that replacement. The Smith cloud will not strike the Milky Way like a rock striking the ground. Gas will meet gas. The leading regions will compress and heat. Shocks will move through both the cloud and the disk. Fragments will slow at different rates. Ionized material will spread across a wider region, and neutral clumps may penetrate farther. Some gas will form shells or cavities. Some will join warm galactic material without producing an obvious structure. The encounter will take place over a long period rather than in one explosion. It also poses no danger to Earth. The projected interaction region is far from the solar system, and the cloud's diffuse gas cannot travel through the outer disk as a solid destructive body. Even if the impact later contributes to new massive stars and supernovae, those events would occur far away and millions of years after the initial mixing began. The phrase collision course attracts attention, but the actual process is a regional gas interaction in the distant future. For the Milky Way, it represents a transfer of fuel. Only a fraction of that fuel is likely to become stars. The gas must cool, become dense, form molecules, and overcome turbulence, pressure, and magnetic support. Some regions may collapse. Others will remain diffuse or return to the halo. The most massive newborn stars would quickly begin heating and dispersing the same gas from which they formed. Star formation regulates itself through this feedback. The Smith cloud therefore carries potential rather than a guaranteed population of 2 million completed stars. Descriptions saying that it contains enough material to form millions of suns compare the cloud's gas mass with the sun's mass. They do not predict that every atom will enter a star. The actual efficiency may be much lower. Even so, a limited conversion would produce a substantial stellar population. Some future stars could contain hydrogen that once belonged to the outer disk, travelled through the halo, mixed with hot coronal gas, and returned in the Smith cloud. The heavier elements could have been created inside still older stars. Dust grains within the incoming material could become part of new protoplanetary disks. The process links several generations without requiring every generation to form in the same place. Matter moves through the galaxy, but it does not arrive at a final state. A hydrogen atom may spend millions of years in diffuse gas, enter a molecular cloud, fall into a star, and later return to space. An oxygen atom may become part of dust, a planet, a stellar atmosphere, or hot plasma. The Milky Way keeps changing how its matter is arranged. The Smith cloud shows one part of that rearrangement in progress. The title of this ending compares the future arrival to gentle rain, but the comparison needs to be kept within limits. The cloud will not fall as liquid droplets. There is no weather system passing above the galactic disk and no surface below it waiting to become wet. The useful part of the comparison is that the material will arrive over an area and over time. The first gas does not wait for the last gas. Smaller fragments reach the Milky Way ahead of the main body. Diffuse layers spread and mix before denser concentrations arrive. The delivery is gradual when measured against the full duration of the event, even though individual shocks may be energetic. Rain also joins an environment that already contains water. Once it enters a river, lake, or soil, identifying each original drop becomes impossible. The Smith cloud's hydrogen will meet the same fate. After it slows and mixes with galactic gas, there will be no permanent marker separating one group of protons from another. Velocity and chemical differences may reveal the incoming material for a while. Eventually, those signatures will become weaker. The Smith cloud will cease to exist as a distinct named structure, while its matter continues inside the Milky Way. That is not destruction in the ordinary sense. The cloud's shape will be destroyed, its coherent motion will be reduced, its gas will remain. Some of it may become stars, some may stay between stars, some may leave the disk again. The object will stop being one thing and become parts of many other things. This has already begun. The tail is losing material. The leading component is interacting with the disk. The main body remains recognizable because enough gas still shares a position and velocity. The distinction will become less clear with time. When astronomers observe the cloud today, they are seeing one stage in a process rather than an object waiting for its process to begin. That may be the most important correction to the original idea. The Smith cloud is not simply on its way to an event. The event is underway throughout its journey. Its movement through the halo is an interaction. The formation of its tail is an interaction. The slowing of fragments is an interaction. The transfer of gas into the Milky Way is already occurring. The future disk crossing is the denser and more disruptive part of a process that started much earlier. This gives the cloud scientific value now. Astronomers can observe how gas approaches a galaxy, how a halo affects it, and how the earliest parts of a larger stream begin joining the disk. They can test theories of cooling, turbulence, magnetic draping, metallicity, and angular momentum transfer. No one needs to observe the cloud for 30 million years to learn from it. Its current shape contains the results of earlier motion, while simulations show how those conditions may develop. Future researchers will improve the picture using instruments that have not yet been built. They may discover more components of the stream, identify a population of faint stars, or place tighter limits on dark matter. They may show that the gas left the outer disk in a superbubble, or that a different interaction created it. Some current ideas will survive, and others will be revised. The radio signal will remain the point from which the investigation began. For the moment, the Smith cloud continues moving. There is no visible streak across the sky. Its position changes far too slowly for anyone to notice over one night. Its hydrogen emits radio waves, and those waves travel toward Earth. When they reach a telescope, the signal contains information about position, velocity, temperature, and structure. The cloud does not know that it has been named, mapped, or placed in computer simulations. It follows gravity and responds to pressure, radiation, magnetic fields, and collisions. Those processes require no observer. What observers add is the ability to connect them. We recognize that the unusual velocity indicates a cloud outside ordinary disk rotation. We recognize that sulfur links it to processed material. We recognize that its tail records drag, and that its magnetic field records the flow around it. The explanation emerges from combining measurements that would look unrelated if considered separately. Radio astronomy sees the neutral gas. Ultraviolet astronomy reads its composition. Optical measurements trace ionized hydrogen. Physics connects all three. This is one reason the universe remains interesting even when the objects cannot be seen directly. Human senses were not designed to detect 21 centimeter hydrogen radiation or ultraviolet absorption lines. Instruments extend those senses, and mathematics turns the results into distances, masses, and velocities. An invisible signal becomes an 11,000 light-year cloud. A shift in frequency becomes a journey through the galactic halo. A missing part of a distant galaxy's ultraviolet spectrum becomes evidence that the cloud has been enriched by older stars. The story is built from measurements rather than from imagination, even though imagination helps us picture the scale. As you rest, the Smith cloud remains far beyond any familiar distance. The room around you may be quiet. A clock may be moving through seconds, or the time may be displayed silently on a nearby screen. The cloud's journey is measured in millions of years, but it is governed by the same continuous passage of physical events. Atoms collide, gas cools, gravity changes motion, radio photons leave hydrogen and begin crossing space. Nothing needs to happen quickly to produce a large result. A tiny drag applied for millions of years forms a tail thousands of light years long. A small frequency shift reveals a speed of hundreds of kilometers per second. A limited abundance of sulfur rules out some possible histories and supports others. The scale changes, but the investigation proceeds one observation at a time. Where are you listening from tonight? Perhaps you're beneath a clear sky, or perhaps clouds in Earth's atmosphere have hidden every star. You may be in a city, a small town near the sea, or somewhere far from streetlights. The Smith cloud lies in the same direction regardless of whether your local sky is visible. It cannot be seen with ordinary eyesight from any location on Earth, but radio telescopes continue receiving its hydrogen signal. What time is it where you are? During the time you've been listening, the Smith cloud has travelled millions of kilometres. That sounds dramatic until it is compared with the thousands of light years remaining in its path. Its progress toward the disk during one evening is too small to change an astronomical map. The motion is still real. Every second adds another few hundred kilometres to the path of its fastest regions. The Milky Way rotates as well. The Sun moves with the disk. Earth travels around the Sun, and the surface beneath you turns with the planet. Rest can feel motionless even when every part of the setting is moving. There is no need to keep track of those motions. The measurements will continue without our attention. Radio surveys will store their data. Hydrogen will keep emitting its narrow line. The galactic halo will continue stripping the cloud's edges, and gravity will continue shaping its route. The future disk encounter requires no preparation from anyone here. It belongs to the long-term activity of the galaxy. For tonight, the Smith cloud can remain what it is, an example of how much lies beyond visible light and how active the apparently empty regions around the Milky Way really are. It is large without being dangerous, fast without arriving soon, and damaged without having disappeared. It contains old galactic material while possibly collecting new halo gas. It is leaving the Milky Way in one version of its past and returning to it in another. Those apparent contradictions are resolved once the cloud is understood as a changing flow rather than a permanent object. If you found this exploration interesting, calming, or useful while settling down, you can give the video a like and subscribe to Science for Sleep. It helps other listeners find this quiet place for long explanations about the universe. You can also leave a comment with your location and the time where you are listening. People in different countries, climates, and time zones can all receive the same story about one radio cloud moving through the same galaxy. By the next time you look at the Milky Way, its bright band will appear much as it did before. The Smith cloud will still be invisible. Its radio outline will still lie beyond ordinary sight. The larger story may now be easier to picture. Around the stars is gas. Around the disk is a halo. Through the halo move clouds, streams, and material pushed outward by earlier generations of stars. Some of that gas returns. Some arrives from farther away. Some mixes until its origin cannot be separated from its destination. The Milky Way is continually receiving and releasing matter. The Smith cloud is one measurable part of that circulation, carrying hydrogen toward a disk that can use some of it again. There is nothing more you need to follow tonight. The main body will not arrive during our lifetimes. No alarm needs to be set for the collision. The cloud will continue moving at its enormous speed, and the remaining distance will continue to require millions of years. Let the numbers become less important now. The object is far away. Earth is safe. The galaxy is behaving normally. Hydrogen moves through the halo. Some of it joins the disk. Over long periods, a small fraction may enter new stars. The radio signal continues crossing space whether anyone listens or not. Here, the explanation can stop while the process continues. Sleep well, fellow traveller, wherever you're listening from, and whatever time your clock happens to show.